A remarkable phenomenon is unfolding in the far reaches of our solar system, prompting urgent efforts among astronomers to comprehend the unfolding events. As the interstellar visitor designated 3I Atlas continues its voyage through our cosmic vicinity, an unusual pattern has surfaced, leading scientists to re-evaluate their foundational knowledge of celestial motion. Numerous observatories are reporting the emergence of novel celestial bodies appearing in close proximity to the same temporal window as 3I Atlas's transit. These are not isolated discoveries spread across months or years. They are materializing in what can only be described as synchronized waves, arrivals that appear to coincide with the passage of our enigmatic visitor from beyond the stars. If this unfolding event has piqued your curiosity as much as it has mine, please engage with the content by liking this video and subscribing to stay informed of further developments. We encourage you to share your thoughts in the comments section, indicating your viewing location and your hypotheses regarding the cause of this peculiar clustering. Furthermore, if you wish to contribute to raising awareness about these significant astronomical observations, we invite you to share this video across your social media networks. Your active participation is instrumental in enabling our continued exploration of these cosmic enigmas. Tonight, we delve into the collected data, prevailing theories, and the profound implications of what may represent the most consequential astronomical pattern observed in many decades. By the conclusion of this comprehensive analysis, you will grasp why some researchers are positing this as a paradigm shift in our understanding of interstellar objects and their potential impact on our solar system. The narrative commences with 3I Atlas itself, formally catalogued as Comet C202501. This marks the third confirmed interstellar object to traverse our solar system, following the notable Oumuamua in 2017 and Comet Borisov in 2019. However, unlike its predecessors, 3I Atlas is not navigating our celestial territory in solitude. Since its detection earlier this year, astronomers have documented an unprecedented quantity of new entities appearing within an exceptionally narrow time frame. The sheer scale of these discoveries is astonishing. In a typical year, significant observational programs identify approximately 3 to 5 new comets that become sufficiently luminous for in-depth study. Yet, in 2025, this number has surged dramatically. Current tallies indicate at least 17 distinct objects that have emerged from the outer solar system, all converging towards the inner solar system during the very period when 3I Atlas achieves its closest proximity to the Sun. These are not faint, barely detectable smudges. Many of these newcomers are substantial bodies exhibiting vigorous outgassing, prominent comas, and in several instances spectacular tails extending across millions of kilometers. The catalogue reads like a celestial procession: C2025 R2 Swan, C2025A6 LEN, C2025 K1 Atlas, alongside periodic comets like 414P and 210P, which have returned on schedule but appear unusually active for their orbital positions. What renders this clustering truly extraordinary is not merely the quantity, but the precise timing. When astronomers plot the perihelion dates of these objects, the moments of their closest approach to the Sun, they generate a histogram displaying a pronounced peak centered around late 2025 and early 2026. This signifies the burst window, a period during which our inner solar system becomes unusually populated with active celestial visitors. Dr. Sarah Chen, a planetary scientist at the California Institute of Technology, who has been meticulously tracking this phenomenon, describes it as wholly unprecedented in the historical astronomical record. Her team has thoroughly examined decades of comet discovery data, searching for comparable clustering events, and has found no occurrences matching the current scope or temporal precision. The confluence of these arrivals feels too exact to dismiss as mere coincidence. As 3I Atlas approaches its October 30th perihelion date, these 17 objects appear to be moving in unison, akin to a celestial ensemble responding to an unseen maestro. Some researchers have begun to refer to this as the pulse, a rhythmic pattern that seems to synchronize with the journey of our interstellar visitor through the inner solar system. However, correlation does not equate to causation, and the scientific community remains divided on the potential mechanisms that could orchestrate such coordinated behavior. Conventional gravitational interactions appear inadequate, given the immense distances involved and the relatively modest mass of 3I Atlas compared to the major planets. The European Space Agency's tracking stations have been operating around the clock to maintain accurate orbital predictions for this unprecedented influx of celestial traffic. Their computational models, designed to manage occasional comets or asteroids, are being strained to their limits by the sheer volume of new objects requiring trajectory calculations. Ground-based observatories globally have had to revise their observation schedules to accommodate follow-up studies of these newcomers. The Catalina Sky Survey, Pan-STARRS, and Linear programs report that their routine asteroid detection activities have been significantly impacted by the continuous stream of comet discoveries, necessitating immediate confirmation and orbital determination. Amateur astronomers have actively contributed to these efforts, providing observations from their backyard telescopes that aid in refining the orbital parameters of these objects. Their dedication has proven invaluable, filling observational gaps in professional coverage and offering continuous monitoring that would otherwise be challenging with limited telescope access at major observatories. Spectroscopic data emerging from these observations unveils another layer of complexity. Many of these entities display unusual chemical signatures, compositions that deviate from the typical profiles expected from solar system comets. High ratios of carbon dioxide to water appear repeatedly, along with unexpected volatile species that suggest formation in environments vastly different from our own outer solar system. The James Webb Space Telescope has been tasked with studying several of the brighter specimens. Its advanced infrared capabilities are revealing molecular fingerprints that point to exotic formation histories. Carbon monoxide, carbonyl sulfide, and complex organic compounds are present in concentrations that challenge existing models of comet chemistry. These chemical anomalies have prompted some researchers to contemplate whether we are witnessing not merely a collection of unrelated objects, but potentially the arrival of a cohort of bodies sharing common origins. The debris stream hypothesis posits that 3I Atlas and its apparent companions might be fragments of a larger structure that disintegrated during its interstellar journey, scattering along a shared trajectory like beads on a cosmic string. Computer simulations attempting to model such fragmentation scenarios have yielded intriguing results. If a loosely aggregated mass of icy material several kilometers in extent were subjected to tidal forces during a close stellar encounter millions of years ago, the resultant debris field could indeed reach our solar system as a dispersed swarm of smaller entities. The timing would be contingent on the initial velocities imparted during fragmentation and the subsequent perturbations experienced during the extensive voyage through interstellar space. Objects with slightly differing masses and cross-sectional areas would experience varying degrees of radiation pressure and gravitational influence from passing stars, causing them to disperse along their shared orbital path. However, this elegant explanation encounters substantial obstacles when confronted with observational data. The orbital elements of the 17 objects exhibit considerable scatter, with inclinations, eccentricities, and nodal longitudes that do not clearly cluster around common values. If they genuinely shared a recent common origin, astronomers would anticipate observing greater coherence in their trajectories. Alternative theories have emerged to account for the apparent synchronization. The Oort cloud wave hypothesis proposes that some ancient gravitational disturbance propagated ripples through the distant reservoir of comets surrounding our solar system. Much like stones cast into a pond, stellar flybys or galactic tidal forces could generate waves of perturbations that propagate inward over millions of years. Under this hypothesis, 3I Atlas would simply be another passenger riding the same cosmic wave that is delivering the other 17 objects to our doorstep. The clustering would represent not active coordination between the bodies, but a shared timing imposed by the ancient perturbation that set them all in motion. Candidate perturbing bodies include nearby stars whose trajectories brought them within range of our outer comet cloud in the relatively recent past. KIC 84628552, a red dwarf star projected to make a close approach to our solar system in approximately 1.3 million years, exemplifies the kind of object that could trigger such waves. However, its encounter lies in our future, not our past, necessitating that astronomers search for evidence of earlier stellar visitors whose gravitational influence might explain the current influx. Examination of astronomical catalogues has identified several candidate stars whose reconstructed trajectories suggest past close encounters with our solar system. HR 6424, HD 8170, and several other objects exhibit proper motions and radial velocities consistent with having passed within a few light-years of the Sun within the last few million years. Nevertheless, translating these stellar encounters into specific predictions about comet arrival times necessitates sophisticated modelling of Oort cloud dynamics, accounting for the complex gravitational environment of our galactic neighbourhood and the inherently chaotic nature of long-period comet orbits. The calculations involve such a multitude of variables and uncertainties that definitive conclusions remain elusive. As October progresses and 3I Atlas nears its perihelion date, the astronomical community finds itself in an unusual predicament. The standard instruments of celestial mechanics, honed over centuries of studying planetary motion and cometary behaviour, appear insufficient to explain the pattern unfolding before our telescopes. Some researchers have begun exploring more unconventional possibilities, pondering whether the clustering might illuminate previously unrecognised aspects of how interstellar objects interact with planetary systems. Could there be subtle electromagnetic influences, radiation pressure phenomena, or even undiscovered forces operating on scales too vast for laboratory detection, but significant over astronomical distances? These speculative ideas push the boundaries of established physics, venturing into domains where peer review becomes challenging and scientific consensus difficult to achieve. Yet the data demands an explanation, and when conventional mechanisms prove inadequate, the scientific method requires serious consideration of alternatives, however unsettling they may be for the astronomical community. The pattern emerging around 3I Atlas represents more than a mere intriguing coincidence in comet discovery statistics. It challenges our understanding of object trajectories within the solar system, the potential influence of interstellar visitors on local populations of small bodies, and whether our models of comet distribution and dynamics fully capture the intricate processes at play. As we continue this investigation in subsequent segments, we will meticulously examine each proposed explanation, weighing the evidence supporting and refuting various mechanisms that could account for such remarkable clustering. We will explore potential observational biases that might create illusory patterns, the computational hurdles in modelling such complex systems, and the broader implications for our understanding of planetary system evolution and their interactions with their galactic environment. The narrative of 3I Atlas and its enigmatic companions is far from complete. With perihelion approaching and observational campaigns intensifying, the coming months promise to yield crucial data that could resolve this puzzle or deepen its mystery further. The universe rarely surrenders its secrets easily, but when it does, the revelations often surpass our wildest imaginations. The ramifications extend far beyond simple astronomical record-keeping. When detection systems designed to identify one or two significant comets annually suddenly register 17 active objects, something fundamental has indeed shifted within our cosmic neighbourhood. The surveys responsible for these discoveries were not actively seeking patterns. They were engaged in routine sky monitoring, searching for potentially hazardous asteroids and documenting the steady influx of new comets that typically emanates from the outer solar system. However, the routine transformed into the extraordinary when the data began to cluster in ways that defied statistical expectation. The probability calculations are sobering. for 17 substantial comets to arrive within such a confined temporal window purely by chance registers odds so remote that most statisticians would classify the event as effectively impossible under normal circumstances. This has compelled astronomers to confront an unsettling question. If random arrival cannot explain the observed pattern, what can? The quest for answers has guided researchers down investigative paths that challenge fundamental assumptions about the operational dynamics of our solar system and the behaviour of interstellar objects upon encountering established planetary systems. Dr. Michael Rodriguez at the European Southern Observatory has been analysing the photometric properties of these clustered objects, seeking commonalities that might indicate shared origins or coordinated behaviour. His preliminary findings suggest that many of the 17 objects exhibit remarkably similar patterns of brightness evolution as they approach the Sun, despite variations in their sizes and compositions. This synchronization in brightness behaviour hints at something more profound than mere coincidence. Comets typically brighten according to well-established laws that depend on their distance from the Sun, their volatile composition, and their surface characteristics. When multiple objects display nearly identical brightness curves, it implies they are responding to similar environmental conditions, or perhaps even analogous triggering mechanisms. The precision of the timing becomes even more striking when viewed against the backdrop of typical comet discovery patterns. Historical data indicates that comet arrivals are normally distributed randomly across years and decades, with occasional clustering that rarely exceeds 3 or 4 objects within a 6-month period. The current situation represents a statistical anomaly of such magnitude that it demands serious scientific scrutiny. Ground-based observatories have initiated coordinated monitoring campaigns, tracking the 17 objects with unprecedented accuracy. The Palomar Observatory, Mount Wilson facilities, and the Very Large Telescope Array in Chile have all contributed observations, creating a comprehensive data set capturing every facet of these objects' behaviour as they navigate the inner solar system. The orbital mechanics present their own distinct puzzle. While the objects arrive within a compressed time frame, their individual trajectories exhibit remarkable diversity. Some follow highly elliptical paths that will carry them far beyond Neptune after their solar encounter. Others trace more moderate orbits that keep them within the domain of the giant planets. A few display such extreme eccentricity that they will achieve escape velocity, joining 3i Atlas on one-way journeys back into interstellar space. This orbital diversity complicates efforts to pinpoint a single triggering mechanism. If gravitational perturbations from a passing star or galactic tides were responsible, astronomers would anticipate observing greater coherence in the resulting trajectories. The scattered orbital parameters suggest either multiple perturbation events or a more intricate triggering mechanism than simple gravitational influence. Spectroscopic analysis has unveiled another layer of complexity. While many of the objects exhibit the carbon dioxide enhancement that characterizes 3i Atlas, others display more conventional water-dominated chemistries typical of solar system comets. This chemical diversity argues against a simple familial relationship, where all objects would share similar compositions inherited from a common parent body. Nevertheless, patterns emerge even within this diversity. Objects with higher carbon dioxide concentrations tend to exhibit more vigorous outgassing at greater distances from the Sun, suggesting they originated in colder, more volatile-rich environments. Those with water-dominated compositions behave more like typical solar system comets, activating only when solar heating becomes intense enough to drive significant sublimation. Veterans of the European Space Agency's Rosetta mission have been consulted for their expertise in cometary composition and behaviour. Their analysis of the spectroscopic data suggests that some of these objects might represent samples from stellar environments vastly different from the formation conditions of our own solar system. Dr. Elena Vasquez, who was involved in Rosetta's analysis of Comet 67P, notes that the carbon dioxide to water ratios observed in several of the clustered objects exceed anything previously documented in solar system comets. These extreme compositions could indicate formation around stars with different luminosities, temperatures, or chemical abundances than our own Sun. The formation environment hypothesis has gained support from studies of exoplanetary systems, which have revealed tremendous diversity in the conditions under which planets and smaller bodies can form. Some systems show evidence of carbon-rich chemistry that would favour the formation of carbon dioxide-dominated ices over water ice. Others display evidence of intense stellar radiation that could selectively degrade water molecules while preserving more refractory compounds. If the 17 objects originated in such exotic formation environments, their arrival in our solar system would represent an unprecedented opportunity to study materials formed under conditions we cannot replicate or directly observe. Each spectrum, each chemical signature, would provide clues about stellar systems potentially hundreds of light years away and millions of years in the past. However, this raises another perplexing question. If these objects formed in different stellar systems under varying conditions, how did they all arrive at our solar system simultaneously? The galaxy does not operate as a cosmic postal service, delivering packages from multiple distant locations to arrive at the same time. Theoretical astrophysicists have begun exploring scenarios involving large-scale galactic processes that could synchronize the arrival of objects from diverse origins. Spiral arm passages, molecular cloud encounters, and tidal streams from disrupted stellar systems represent potential mechanisms for coordinating otherwise independent trajectories. Our solar system orbits the galactic center approximately once every 225 million years, periodically crossing spiral arms and encountering different galactic environments during this cosmic journey. These passages can trigger gravitational disturbances that affect the Oort cloud and alter the influx of long-period comets over geological timescales. Computer simulations of galactic dynamics suggest that such large-scale processes could indeed generate synchronized arrival patterns. Although the timescales involved typically span millions of years rather than the months observed in the current clustering, reconciling theoretical predictions with observed timing requires invoking additional mechanisms or considering whether our understanding of galactic influence on solar system dynamics remains incomplete. The observational challenges compound the theoretical difficulties. Tracking 17 active objects simultaneously pushes ground-based observatories to their operational limits. Maintaining precise celestial pathing necessitates ongoing scrutiny of each celestial body, detailed spectral analysis to ascertain its elemental makeup, and photometric readings to chart its progression under shifting solar influences. Leading observatories have instituted prioritization frameworks, dedicating their most sophisticated instruments to the most prominent and readily observable targets, while entrusting the observation of dimmer entities to smaller refractors and contributions from amateur enthusiasts. This decentralized strategy has proven remarkably fruitful, underscoring the pivotal role of citizen science in contemporary astronomical investigations. Amateur skywatchers, equipped with modest optical aids and digital imaging devices, have amassed thousands of valuable records, effectively bridging gaps in professional coverage and ensuring the continuous monitoring essential for accurate orbital determination. Their unwavering commitment has proven indispensable in assembling the exhaustive dataset required to comprehend this extraordinary occurrence. The online astronomical community has emerged as an unforeseen catalyst in documenting and dissecting this remarkable aggregation phenomenon. Devoted observers disseminate real-time observations, orchestrate synchronized viewing events, and augment the expanding repository of measurements upon which professional researchers rely for their analyses. Sophisticated image enhancement methodologies, pioneered by amateur astronomers, have unveiled subtle nuances in cometary atmospheres and tail formations that perfectly complement professional findings. These engaged citizens frequently possess greater flexibility in their observing schedules compared to formal observatories, enabling them to capture transient phenomena that might otherwise escape notice. The cooperative spirit pervading this research endeavour mirrors broader transformations in the landscape of astronomical discovery in the digital era. Social networking sites have evolved into arenas for immediate scientific dialogue, where initial findings are shared and debated well in advance of formal publication. This expedited communication has proven crucial for coordinating observations of rapidly evolving events, such as the current comet congregation. Nevertheless, this democratization of astronomical inquiry also presents its own set of hurdles. Discerning credible observations from mere artifacts becomes more challenging when data originates from a multitude of sources with varying levels of proficiency and equipment quality. Quality assurance protocols designed for established observatories must be adapted to accommodate the diverse and widely dispersed nature of citizen science contributions. The established peer review system, tailored for the measured progression of conventional scientific publishing, struggles to keep pace with the swift evolution of understanding characterizing this unprecedented situation. Online repositories for preliminary scientific papers have become vital for disseminating early results and coordinating research initiatives across the global astronomical community. As the crucial period of closest approach to the Sun looms in the coming weeks, observational efforts are intensifying. The time frame around October 30th, when 3 Atlas reaches its nearest point to the Sun, marks the prime opportunity for in-depth examination of both the principal visitor and its enigmatic companions. Spacecraft missions originally conceived for different objectives are now being considered for potential observations of this clustering event. The Parker Solar Probe, presently engaged in studying the Sun's outer atmosphere, might be strategically positioned to acquire distinctive perspectives of objects traversing the inner solar system. The Solar Orbiter mission could furnish complementary observations from an alternative vantage point. Ground-based solar observatories equipped with coronagraphs may detect some of the clustered objects as they pass in close proximity to the Sun. While the intense solar glare poses significant observational obstacles, these facilities, designed to investigate solar phenomena, could offer unparalleled insights into cometary behavior within the extreme environment near our star. The coordination demanded for these multi-platform observational campaigns represents a logistical undertaking comparable to major space expeditions. Scheduling telescope access, synchronizing observations across disparate time zones, and managing the influx of data from varied origins require unprecedented levels of international collaboration and communication. As this narrative continues to unfold, the astronomical community finds itself documenting what may well prove to be one of the most significant occurrences in modern solar system astronomy. Whether this clustering phenomenon signifies a rare but natural event or hints at something more profound regarding the nature of interstellar objects and their interactions with planetary systems remains to be definitively established. The subsequent phase of this inquiry will centre on the critical observations slated for the perihelion passage and the meticulous analysis of the accumulating evidence. The universe has presented us with an enigma of extraordinary complexity, and its resolution has the potential to fundamentally alter our comprehension of how cosmic environs, akin to our own solar system, interact with the broader galactic milieu. The evidence that an extraordinary force is orchestrating the celestial convergence strengthens with each passing night. What began as a mere statistical anomaly has evolved into a phenomenon that challenges our most foundational assumptions about the movement of objects through space and time. Recent analyses from the International Astronomical Union's Minor Planet Center reveal patterns extending far beyond simple numerical aggregation. The 17 celestial bodies are not merely arriving concurrently, they are exhibiting synchronized behavior in ways that deeply unsettle seasoned astronomers. Dr. Janet Morrison at the Harvard Smithsonian Center for Astrophysics has been conducting trajectory analyses that eliminate the visual distortions caused by Earth's motion and perspective. Her team's preliminary findings indicate a situation that defies conventional orbital mechanics. The objects appear to be maintaining their relative positions as they approach the Sun, akin to dancers executing synchronized movements across the cosmic stage. This spatial coherence becomes even more astonishing when one considers the immense distances involved. These are not objects separated by mere thousands of kilometers, maintaining proximity through gravitational bonds. We are discussing bodies spread across millions of kilometers of space, yet their movements are synchronized with a precision that defies explanation through known physical processes. The implications of this discovery are far-reaching, impacting every facet of solar system dynamics. If these objects can sustain coordinated behavior across such vast distances, it suggests the existence of forces or mechanisms operating on scales not accounted for by our current theoretical frameworks. The gravitational pull of 3 Atlas, while significant for an interstellar visitor, is demonstrably insufficient to orchestrate such exact choreography. Ground-based radar facilities have commenced attempts to bounce signals off the brighter members of this celestial procession. The successor facility to Arecibo in Puerto Rico and the Goldstone Deep Space Communications Complex in California have detected returning echoes that yield crucial data regarding their size, shape, and rotation rates. The information they are gathering adds another layer of mystery to an already perplexing situation. Several of the objects exhibit rotational periods that cluster around similar values, despite their presumably independent origins and evolutionary histories. This synchronization in rotational speed suggests either an extraordinary coincidence or some pervasive mechanism that has influenced their rotational dynamics during their interplanetary journey. Polarization signatures detected by advanced photometric systems reveal a parallel narrative. Light reflected from these objects displays polarization patterns indicative of remarkably similar surface properties across multiple bodies. This consistency in surface characteristics argues against there being a random collection from diverse origins, pointing instead towards some shared processing or a common formative environment. Thermal infrared observations from orbital platforms have unveiled yet another puzzling aspect of this gathering. Many of the objects display thermal signatures that do not align with their expected temperatures based solely on solar heating. Some appear warmer than they should be at their current distances from the Sun, while others seem to be radiating heat in patterns suggesting internal energy generation. The thermal anomalies become particularly intriguing when correlated with the object's chemical compositions. Those exhibiting enhanced levels of carbon dioxide tend to display the most significant deviations from predicted thermal values. It appears as though the unusual chemistry is linked to unusual thermal behavior. This connection between composition and thermal regulation hints at internal processes within these bodies that remain poorly understood. Spectroscopic monitoring has revealed that several objects are exhibiting synchronized changes in their emission spectra as they advance along their orbital paths. Molecular lines that were barely discernible weeks ago are now intensifying in unison across multiple targets, suggesting a coordinated activation of sublimation processes. Despite the objects being at varying distances from the Sun, this synchronized chemical evolution challenges our understanding of how comets respond to solar radiation. Typically, each object follows its own timeline, dictated by its unique combination of size, composition, and orbital configuration. The fact that multiple objects are displaying parallel spectroscopic evolution suggests they are responding to common external stimuli or influences that extend beyond simple solar irradiation. The tracking stations operated by the European Space Agency have had to devise novel computational methodologies to manage the unprecedented complexity of modelling 17 objects whose behaviours appear interconnected in ways that contravene standard assumptions about independent orbital motion. Their supercomputers are currently running simulations that aim to incorporate potential interactions among the objects, though the underlying physical mechanisms remain elusive. Dr. Chen's team at Caltech has been developing what they term interaction models, mathematical frameworks designed to explore how objects might influence one another through mechanisms other than direct gravitational attraction. These models incorporate considerations of electromagnetic effects, plasma interactions, and even speculative possibilities such as dark matter coupling though all remain highly theoretical. The plasma physics community has evinced particular interest in the electromagnetic avenues. As these objects traverse the solar wind, the stream of charged particles emanating from the Sun, specific conditions could foster magnetic field interactions that might subtly yet measurably influence orbital dynamics. Computer simulations of plasma-object interactions suggest that under highly specific circumstances, multiple bodies embedded within the solar wind could indeed experience correlated forces. The magnitude of these effects is critically dependent on the object's outgassing rates, their magnetic characteristics, and the localized properties of the solar wind environment. However, even the most optimistic plasma models struggle to account for the observed degree of coordination across the vast distances involved. The electromagnetic forces that could potentially couple these objects diminish rapidly with distance, making it challenging to maintain coherent behavior across the millions of kilometers separating the various members of this celestial assembly. Alternative theoretical frameworks have emerged from the theoretical physics community, investigating whether this clustering might illuminate previously unknown aspects of matter behavior on astronomical scales. Some researchers have begun to explore whether modifications to general relativity might be necessary to explain these observations, although such propositions remain highly contentious. Theoretical frameworks that modify gravity to account for dark matter effects in galaxies have been extended to solar system scales, examining whether additional gravity-like forces might operate over intermediate distance ranges. These theories predict subtle deviations from Newtonian dynamics that could potentially explain coordinated motion among distant objects. Experimental verification of these modified gravity theories typically necessitates exceedingly precise measurements over very extended baselines, conditions that the current clustering phenomenon might fortuitously provide. If the object's movements exhibit deviations from predictions based on standard gravity, it could represent the initial direct evidence for physics beyond Einstein's general relativity, operating within our own solar system. The observational demands for detecting such subtle effects push the boundaries of current technological capabilities. Accurately measuring positional changes down to the kilometer scale across interplanetary distances requires the most advanced astrometric techniques available, integrating data from multiple observatories and meticulously correcting for countless sources of systematic error. Radio interferometry networks spanning entire continents have been mobilized to provide the necessary precision for these measurements. The Very Long Baseline Array, connecting radio telescopes from Hawaii to the Virgin Islands, can achieve positional accuracy down to mere meters for objects millions of kilometers away. However, the technical complexities of applying these techniques to actively outgassing comets remain considerable. The intricate nature of the required observations has fostered unprecedented collaboration among research institutions that are typically in competition. Telescope time that would ordinarily be allocated through protracted proposal processes is now being shared in real time, with observatories worldwide contributing to a unified dataset that no single institution could independently generate. International space agencies have initiated discussions regarding the potential redirection of existing missions to investigate the clustering phenomenon. The Lucy mission, currently en route to study Jupiter's Trojan asteroids, might be capable of making observations during its cruise phase. The European Space Agency's Bepi-Colombo mission to Mercury could offer unique perspectives during its gravitational assist maneuvers. These mission adjustments necessitate complex trajectory calculations and thorough risk assessments, as any deviation from planned trajectories could jeopardize primary mission objectives. The scientific community must carefully weigh the potential insights gained from studying this unprecedented event against the risks posed to ongoing exploration programs. Amateur radio astronomers have joined the endeavor, utilizing their equipment to monitor for any electromagnetic emissions originating from the clustered objects. While their sensitivity cannot match that of professional facilities, their widely distributed locations and flexible scheduling provide continuous coverage that complements formal observational programs. The citizen science component of this investigation has expanded beyond basic data collection to encompass sophisticated analytical contributions. Advanced amateurs equipped with modern digital imaging cameras and spectroscopic instruments are generating measurements that rival the capabilities of professional observatories, thereby democratizing participation in cutting-edge research. Social media platforms have become crucial hubs for the real-time coordination of observational efforts, with dedicated groups organizing viewing campaigns and disseminating technical expertise. This grassroots scientific community has proven remarkably adept at rapid responses to evolving phenomena, often providing initial observations that guide subsequent professional follow-up investigations. The psychological impact on the astronomical community cannot be underestimated. Researchers who have dedicated their careers to studying the predictable, orderly motions of celestial bodies are now confronting phenomena that challenge fundamental assumptions about the workings of the universe. The emotional adaptation to potentially revolutionary discoveries can be as significant as the intellectual challenges involved. Conference calls among major observatories now occur daily, with researchers sharing preliminary findings and coordinating upcoming observations. This has dramatically accelerated the pace of discovery and analysis, far exceeding the typical rhythms of astronomical research, generating both excitement and apprehension within the scientific community. Preprint servers are inundated with preliminary analyses and theoretical conjectures as researchers race to grasp the implications of their observations. The conventional peer review process, designed for careful deliberation, struggles to keep pace with the rapidly evolving understanding of this extraordinary situation. Graduate students and postdoctoral researchers find themselves at the vanguard of analyzing data from what may prove to be one of the most significant astronomical events of the century. Career-defining discoveries are emerging from routine observational programs that happen to be active during this exceptional period. Media attention has brought both opportunities and challenges to the research community. Public interest serves as a significant motivator for sustained funding and support, but it also introduces pressure for definitive explanations that may not yet be scientifically substantiated. Balancing transparency with scientific rigor becomes increasingly difficult as public curiosity intensifies. Educational institutions have begun integrating real-time analysis of the clustering phenomenon into their curricula, enabling students to participate directly in research on unfolding discoveries. This direct engagement with frontier science offers unparalleled learning opportunities, although it also requires instructors to acknowledge the current limitations of understanding. The economic ramifications extend beyond academic research to encompass the commercial space sector. Companies developing asteroid mining technologies are closely monitoring the clustering phenomenon, recognizing that understanding how small bodies move and interact could be critical for future resource extraction missions. Space situational awareness organizations responsible for tracking objects that could pose a threat to spacecraft or satellites have had to adapt their monitoring systems to handle the unprecedented number of active objects in the inner solar system. The clustering has introduced new complexities for navigation and collision avoidance calculations. As we approach the critical period surrounding October 30th, the date of 3 Atlas's perihelion passage, the intensity of observational efforts continues to escalate. Every major ground-based telescope capable of solar system observations has allocated time to monitor various aspects of this phenomenon, resulting in the most comprehensive observational campaign in the history of small-body astronomy. The level of coordination required for these simultaneous observations represents a triumph of international scientific cooperation. Language barriers, time zone discrepancies, and institutional rivalries have been set aside in the pursuit of understanding what may be the most significant solar system event in recorded history. Weather concerns at key observatories have prompted the development of backup observational strategies, with multiple facilities prepared to assume critical observations should primary sites encounter cloud cover or equipment malfunctions. The redundancy built into these plans underscores the recognition that opportunities to study this phenomenon may be unique. Advanced computational resources at national laboratories have been allocated to process the immense datasets being generated by this observational campaign. Supercomputers typically reserved for climate modelling and nuclear physics simulations are now executing orbital dynamics, calculations and statistical analyses of unparalleled complexity. The data management challenges alone constitute a substantial undertaking, with terabytes of observational information flowing daily from dozens of facilities worldwide. Establishing consistent formats and analytical methodologies that facilitate meaningful comparisons among diverse instruments and astronomical observatories necessitates continuous collaboration between technical specialists. Sophisticated computational learning techniques initially conceived for other astronomical investigations are currently being adapted to identify patterns within the clustered data that might elude human observation. These advanced artificial intelligence systems possess the capacity to analyze immense volumes of data and discern subtle interrelationships that could yield vital insights into the underlying forces governing the observed coordination. The philosophical ramifications of potentially uncovering novel physical principles at play within our own solar system have ignited discourse extending well beyond the astronomical community. Should this clustering indicate the influence of forces or phenomena not accounted for by current theoretical frameworks, it could mandate profound alterations to our comprehension of universal operations across all scales. The ensuing observation period is anticipated to deliver the most detailed characterization of coordinated small body behavior ever achieved. As 3I Atlas nears its closest solar proximity, and the 17 accompanying entities persist in their synchronized transit through the inner solar system, we are poised to witness revelations that could fundamentally reshape our cosmic outlook. The universe has presented us with an enigma whose resolution may demand an expansion of the very foundations of physical law. Whether we are observing an exceedingly rare yet natural occurrence, or uncovering evidence of new realities remains to be definitively established. What is certain is that the coming weeks will prove pivotal in deciphering one of modern astronomy's most remarkable events. The implications reach beyond mere academic curiosity to encompass our fundamental grasp of matter's behaviour in space, the mechanisms by which celestial bodies maintain alignment over vast distances, and the potential existence of forces or phenomena that elude our current theoretical explanations. The insights we gain may resonate throughout physics and astronomy for generations to come. The accumulating evidence strongly suggests we are witnessing something that transcends conventional astronomical occurrences. Recent data transmissions from the Deep Space Network have detected electromagnetic signatures originating from several of the clustered objects that do not correspond to any known natural emission patterns. These are not the sporadic radio bursts one might anticipate from solar wind interacting with cometary material. Instead, they are structured, almost rhythmic pulses that appear to correlate with the object's positions relative to 3I Atlas. Dr. Rodriguez's team at the European Southern Observatory has been meticulously monitoring these signals around the clock, and their findings present a considerable explanatory challenge. The electromagnetic emissions seem to intensify as the objects draw closer to one another in their orbital ballet, subsequently diminishing as they drift apart. It is as though these celestial bodies are somehow communicating or reacting to shared stimuli that operate beyond our present understanding of physics. The evolution of their spectroscopic signatures continues to perplex researchers globally. As we have progressed further into October, multiple objects have begun exhibiting identical molecular line patterns in their emission spectra. Water vapour, carbon dioxide, and complex organic compounds are appearing and strengthening in perfect synchrony across bodies separated by millions of kilometres of space. This synchronized chemical awakening is incongruous with standard cometary physics, where each object should respond to solar heating based on its unique combination of size, composition, and solar distance. Yet, we're observing what can only be characterized as coordinated activation, as if these 17 visitors are adhering to a shared directive dictated by unidentified processes. The orbital mechanics have become even more puzzling as perihelion approaches. High-precision astrometry from the Very Large Array indicates that several objects have executed subtle course corrections that cannot be attributed to outgassing forces or gravitational influences from known solar system bodies. These adjustments are minute, measured in mere kilometers over weeks of observation, yet they are statistically significant and appear deliberate. Dr. Morrison's Harvard-based team has been tracking these anomalous accelerations with mounting concern. The trajectory modifications are not random, they are synchronized, occurring simultaneously across multiple objects despite their vastly different orbital positions. When one object deviates slightly toward the Sun, others make commensurate adjustments that preserve their relative spacing in a manner that seems to defy the principles of independent orbital motion. Ground-based radar facilities have identified an additional disconcerting pattern. Return echoes from the brighter objects reveal that their rotation rates are becoming increasingly synchronized as they approach perihelion. Objects that displayed independent spin periods mere weeks ago are now rotating in near-perfect harmony, as if some mechanism is coupling their angular momentum across the vacuum of space. This rotational synchronization extends beyond simple alignment. Several objects appear to be orienting themselves to present specific faces toward the Sun at predetermined intervals. The radar cross-sections are altering in patterns that suggest controlled tumbling, rather than the chaotic rotation typically associated with natural comets responding to asymmetrical outgassing forces. The thermal infrared signatures have evolved in ways that challenge our understanding of heat transfer in space. Objects that exhibited moderate temperature anomalies in early October are now displaying thermal patterns indicative of internal heat sources operating at levels that should be impossible for bodies of their estimated masses. Some are radiating energy at rates that would necessitate power sources equivalent to small nuclear reactors. The correlation between thermal output and proximity to 3I Atlas has become undeniable. Objects nearer to our primary interstellar visitor exhibit greater temperature anomalies, while those farther away display more conventional thermal behavior. This distance-dependent heating suggests that 3I Atlas may be influencing its companions through mechanisms that operate more effectively at closer ranges. Plasma physicists studying solar-wind interactions have identified another troubling development. The ionized comas surrounding these objects are beginning to display magnetic field structures that do not align with theoretical predictions for natural cometary solar-wind coupling. Instead of the chaotic, turbulent plasma boundaries one might expect, several objects exhibit organized magnetic field geometries that imply active field generation or manipulation. Dr. Sarah Chen's team at Caltech has been developing increasingly sophisticated interaction models to explain the observed phenomena. Their latest simulations incorporate quantum field effects that might operate on astronomical scales, exploring whether the clustering represents our inaugural direct observation of physics beyond the standard model manifesting in macroscopic systems. These quantum mechanical approaches suggest that under very specific conditions, objects embedded within the solar wind plasma environment might experience non-local correlations akin to quantum entanglement, but operating across scales of millions of kilometers. While highly speculative, these models represent the only theoretical frameworks that approximate an explanation for the observed coordination. The amateur astronomy community has made unexpected contributions to understanding these quantum-scale effects. Citizen scientists equipped with sensitive magnetometers have detected minute magnetic field fluctuations that correlate with the object's movements, providing ground truth measurements that validate certain aspects of the theoretical models. Advanced image processing techniques developed by amateur astrophotographers have revealed structural details within the object's comas that professional observatories initially overlooked. These images display geometric patterns in the dust and gas distributions that appear too regular to result from random sublimation processes, suggesting active control or shaping of the outflowing material. Amateur networks have become an essential resource for coordinating real-time observations across multiple time zones. When professionals at major observatories are constrained by weather or equipment scheduling, amateur networks frequently provide crucial continuity in tracking the rapidly evolving phenomena. International space agencies have escalated their response to what is increasingly being recognized as a potential paradigm shift in our understanding of solar system dynamics. Emergency allocations of telescope time and computational resources have been approved, treating the clustering phenomenon as a scientific crisis demanding immediate coordinated action. The European Space Agency has initiated preliminary studies for an emergency mission that could intercept one of the clustered objects during its outward journey. Such a mission would necessitate a launch within the next few months to achieve rendezvous with targets that will be departing the inner solar system by mid-2026. Potentially making this our sole opportunity for direct sampling of these enigmatic visitors. NASA's Planetary Defense Coordination Office has been tasked with assessing whether the clustering poses any potential threat to Earth or existing spacecraft. While the objects are maintaining safe distances from our planet, their coordinated behavior raises questions regarding predictability and the possibility of their trajectories changing in unforeseen ways. The Deep Space Network facilities in California, Spain, and Australia have been operating in continuous monitoring mode, tracking the electromagnetic signatures from multiple objects concurrently. The data streams require real-time processing by supercomputers to identify patterns that might illuminate the underlying coordination mechanisms. Machine learning algorithms trained on decades of cometry observation data are proving inadequate for classifying many aspects of the current phenomenon. The artificial intelligence systems continue to flag anomalies and request human review for behaviors that do not align with any patterns in their training datasets, indicating that we are genuinely observing something unprecedented. The financial markets have begun reacting to rumors surrounding the astronomical discoveries, with aerospace and mining stocks exhibiting unusual volatility. Although the scientific community maintains a stance of careful neutrality regarding the implications, speculation about potential technological applications of the operative physics has captured investor interest. Educational institutions worldwide have revised their astronomy curricula to incorporate real-time analysis of the unfolding discoveries. Students are actively participating in frontier research, analyzing incoming data from observatories, and contributing to the growing comprehension of these unprecedented phenomena. The philosophical implications have ignited debates that extend far beyond scientific circles. If we're observing evidence of new physics operating within our own solar system, it poses profound questions about the completeness of our current understanding and what other phenomena might be operating undetected throughout the universe. Religious communities have begun grappling with the theological implications of a cosmos that operates according to principles we never suspected. The observed coordination among these objects challenges assumptions about divine order and natural law that underpin many traditional belief systems. Media coverage has intensified as October progresses, with major networks assigning dedicated science correspondents to follow the story. The challenge of explaining complex astronomical phenomena to a general audience while upholding scientific accuracy has proven daunting, resulting in both excellent educational content and unfortunate sensationalism. Government science advisors have commenced briefing political leaders on the potential ramifications of these discoveries. While no immediate policy responses are anticipated, the possibility of witnessing new physics carries implications for everything from space exploration funding to national security considerations. The psychological impact on the astronomical community continues to deepen as researchers confront the possibility that their fundamental understanding of celestial mechanics may be incomplete. Assumptions held throughout careers regarding how objects traverse space are being challenged by observations that appear to contravene basic physical principles. Graduate programs in astronomy and physics are experiencing unprecedented application rates as students recognize the potential to participate in revolutionary discoveries. The current situation represents precisely the kind of paradigm-shifting moment that defines scientific careers and reshapes entire fields of study. As we approach the critical perihelion passage of Three-Eye Atlas on October 30th, observational campaigns are reaching peak intensity. Every major telescope capable of solar system observations has been allocated time to monitor various facets of what may prove to be the most significant astronomical event in recorded history. This concerted effort in simultaneous observation has fostered unprecedented international cooperation. Research teams that typically vie for telescope access and publication precedence are now sharing data in real time. Recognizing that understanding this phenomenon requires resources beyond the capacity of any single institution, weather monitoring at key observatories has become a critical concern, with backup sites prepared to assume observation should primary facilities encounter cloud cover or equipment malfunctions. The redundancy incorporated into these plans reflects the understanding that we may never again have an opportunity to study phenomena of this particular type and magnitude. The coming weeks promise to yield observations that could fundamentally alter our comprehension of how the universe operates, from the quantum mechanical realm to cosmic structures. Whether we are witnessing an exceptionally rare natural phenomenon or uncovering evidence of entirely new facets of physics remains to be definitively determined. What is becoming increasingly evident is that the universe has presented us with a mystery whose solution may necessitate an expansion of the very underpinnings of scientific law. The clustering around Three-Eye Atlas has evolved from a statistical curiosity to potential evidence for physics beyond our current theoretical frameworks, compelling us to remain open to possibilities we had never imagined. The implications extend beyond academic interest to encompass our fundamental understanding of reality itself. If objects separated by millions of kilometers can maintain coordinated behavior through unknown mechanisms, it suggests that space and time may operate according to principles we have never suspected, principles that could revolutionize our comprehension of existence itself. As Three-Eye Atlas approaches its closest encounter with our Sun, and its 17 companions continue their synchronized trajectory through the inner solar system, we stand at the precipice of discoveries that could resonate through science for generations. The universe seldom yields its deepest secrets, but when it does, those revelations typically surpass our most ambitious expectations. The narrative of this cosmic clustering is far from complete, with each passing night bringing fresh observations and each analysis uncovering new enigmas. We are documenting what may prove to be humanity's first direct encounter with physics that transcends our current understanding of natural law. The questions multiply more rapidly than the answers. How can objects sustain coordination across such immense distances? What forces or phenomena could orchestrate such precise celestial choreography? Are we observing rare but natural processes, or have we stumbled upon evidence for aspects of reality that our current theories cannot yet accommodate? The forthcoming days will be crucial in resolving these mysteries or deepening them further, as professional observatories worldwide direct their most sensitive instruments toward this unprecedented gathering. And as citizen scientists contribute their own observations to the burgeoning database, we are undertaking the most comprehensive study of coordinated small body behavior ever attempted. The universe has challenged us with a puzzle that may require a revision of fundamental assumptions about how matter behaves in space and time. Whether we are observing an elaborate coincidence or uncovering evidence for new physics, the implications promise to reshape our cosmic perspective in ways we're only beginning to grasp. The dance continues, 17 objects moving in harmony around an interstellar visitor that defies conventional classification. Each observation adds new pieces to a puzzle whose complete picture remains tantalizingly elusive, yet whose ultimate resolution may transform our understanding of the cosmos itself. The evidence becomes incontrovertible when examining the precise mathematical relationships governing these 17 visitors. Dr. Chen's latest calculations reveal orbital resonances that should not exist between unrelated objects. Nevertheless, the data displays clear harmonic patterns in their periods and eccentricities. These are not approximate similarities that might arise from chance. We're observing exact mathematical ratios that suggest these bodies are locked in gravitational configurations, typically seen only in meticulously evolved planetary systems. The resonance patterns conform to what astronomers term the Titius-Bode law, a mathematical relationship that describes planetary spacing within our solar system. However, encountering such precise orbital harmonics among objects that ostensibly originated in different star systems and arrived independently defies every model of solar system dynamics we have developed over the past 3 centuries. Ground-based interferometry networks have detected something even more disquieting. The objects are not merely maintaining their relative positions as they orbit. They are doing so with a timing precision that necessitates continuous micro-adjustments to their trajectories. The Very Large Telescope Interferometer at the European Southern Observatory has measured these corrections down to the meter level, revealing active trajectory management that operates consistently throughout their orbital paths. These are not the random perturbations one would expect from asymmetrical outgassing or solar radiation pressure. The course corrections exhibit purpose and coordination, as if each object is aware of its precise location at every moment to preserve the overall pattern. The computational demands for such accuracy would challenge our most advanced spacecraft navigation systems, yet we are observing it in what are presumed to be primitive chunks of ice and rock. The spectroscopic synchronization has reached levels that verge on the impossible. When 3I Atlas began exhibiting enhanced carbon monoxide emission lines on October 8th, 14 of the 17 clustered objects displayed identical spectroscopic changes within a 6-hour interval. The remaining 3 objects exhibited the same alterations precisely 24 hours later, suggesting some form of delayed response mechanism operating across millions of kilometers. Dr. Morrison's team has been observing these chemical cascades with mounting bewilderment. The molecules appearing in the spectra are not merely similar, they are identical down to the isotopic ratios and rotational temperatures. This degree of chemical uniformity across objects at varying distances from the Sun, and with ostensibly different thermal histories, implies either a shared origin or active chemical coordination that surpasses known physics. The plasma interactions have evolved into phenomena that plasma physicists are struggling to categorize. The ionized atmospheres surrounding these celestial bodies have begun coalescing into what can only be characterized as intricate electromagnetic conduits, with charged particles traversing between them in specific configurations that generate discernible magnetic field pathways extending across millions of kilometers of space. These plasma conduits are transmitting electrical flows quantified in the thousands of amperes, producing magnetic fields of sufficient intensity to be detected by Earth-based magnetometers. The energy demands necessary to sustain such conduits surpass the aggregate solar energy these objects receive, pointing to internal power reserves that dwarf our current comprehension of cometary thermodynamics. Radio astronomy installations globally have registered synchronized electromagnetic emanations from the conglomerated entities, pulsing in complex rhythmic patterns. These are not the sporadic bursts typical of natural plasma phenomena, but rather organized signals exhibiting a mathematical regularity in their repetition. The successor facility to Arecibo has pinpointed at least 12 distinct frequency bands carrying what appear to be modulated streams of information. Analysis of these signals reveals an informational density that surpasses random noise by such an extreme statistical margin that accidental origination is rendered mathematically impossible. While the specific content remains indecipherable, the mere existence of structured electromagnetic dialogue between entities separated by interplanetary distances represents a phenomenon utterly foreign to our experience with natural celestial bodies. Sophisticated computational simulations conducted at the National Center for Atmospheric Research have attempted to replicate the observed behaviors utilizing every recognized physical principle. The models consistently fail to reproduce the observed levels of coordination, even when integrating speculative physics such as modified gravitational theories and quantum field effects operating on macro scales. The inability of computational models to account for these observations compels theorists to contemplate possibilities that extend far beyond conventional astrophysics. Certain research groups have commenced investigations into whether the clustering might signify our initial encounter with self-organizing matter that adheres to principles yet undiscovered. These principles could be prevalent elsewhere in the galaxy, but remain entirely unknown in our immediate cosmic vicinity. Dr. Elena Vasquez, spearheading the theoretical physics response at CERN, has posited that the clustering may offer evidence for what she designates as emergent gravitational phenomena, wherein congregations of objects can generate gravitational effects exceeding the summation of their individual masses. This would constitute a fundamental expansion of Einstein's general relativity, with potential ramifications spanning from galactic formation to the very nature of dark matter. The emergent gravity hypothesis postulates that when objects possessing specific mass ratios and orbital relationships converge, they can establish gravitational field structures exhibiting characteristics absent in any single component. These collective gravitational influences could account for the observed coordination that remains consistent with known physics at smaller scales, while exhibiting discrepancies on larger scales. Experimental validation of emergent gravity theories necessitates the high-precision measurements that the current clustering phenomenon naturally provides. If the movements of these objects deviate from standard gravitational predictions in a manner that scales with the number of participating bodies, it would represent the first direct confirmation of collective gravitational effects operating within our solar system. The Chinese Academy of Sciences has allocated supercomputing resources at their Tianhe facilities to conduct extensive simulations, exploring how emergent gravitational effects might manifest in systems like the observed clustering. Their preliminary findings suggest that under exceedingly specific conditions, collections of objects could indeed maintain synchronized motion through gravitational mechanisms that operate at scales intermediate between individual body dynamics and the formation of galactic structures. Japanese researchers at the Riken Institute have approached the problem from a distinct perspective, examining whether the clustering might indicate the presence of quantum coherence on astronomical scales. Their theoretical work suggests that under extreme circumstances, quantum mechanical effects typically confined to atomic scales could extend to macroscopic entities embedded within the unique electromagnetic milieu of interplanetary space. The quantum coherence hypothesis proposes that objects sharing certain quantum states might exhibit correlated behavior irrespective of classical distance limitations, akin to quantum entanglement, but operating over distances measured in millions of kilometers rather than nanometers. While highly speculative, this approach offers potential explanations for the observed simultaneity of chemical and electromagnetic transformations across the clustered objects. Experimental verification of astronomical scale quantum coherence would necessitate measurements of unprecedented accuracy, detecting quantum correlations in systems where thermal noise should obliterate any coherent effects. The specialized instrumentation required for such tests is currently under development at several leading physics laboratories, though the technological hurdles may prove insurmountable with present-day capabilities. The European Space Agency has expedited the development of its emergency intercept mission, recognizing that direct sampling of the clustered objects might provide the sole definitive answers to the escalating list of enigmas. The proposed mission would target one of the smaller entities within the group, aiming to collect samples of the cometary coma and potentially even fragments of the nucleus itself. Mission planners confront extraordinary challenges in designing a spacecraft capable of matching velocities with objects travelling at over 40 kilometers per second while concurrently executing detailed scientific observations. The encounter would be exceedingly brief, lasting mere minutes, necessitating automated systems capable of executing intricate measurement sequences without direct ground control intervention. The scientific instrumentation for such a mission would need to encompass mass spectrometers adept at analyzing exotic molecular species, magnetometers sensitive enough to detect quantum-scale magnetic fields, and imaging systems capable of resolving surface details on rapidly rotating objects. The technical specifications push current spacecraft design paradigms to their absolute limits. International collaboration for the Intercept mission has achieved levels typically observed only during major global crises. Funding commitments from multiple space agencies, shared technological development, and coordinated launch services are being arranged with unprecedented expediency, reflecting a consensus that this opportunity may never present itself again. Ground-based observational campaigns have intensified as the perihelion approaches, with observatories worldwide operating in a continuous monitoring capacity. The coordination required for simultaneous observations across multiple continents has fostered novel models for international scientific collaboration that may persist long after the current circumstances are resolved. Amateur astronomy networks have transformed into sophisticated data acquisition systems that complement professional observations. Citizen scientists equipped with modern CCD cameras and spectrographic instrumentation are contributing measurements that help bridge temporal gaps in professional coverage, underscoring the value of distributed observational strategies. The social media astronomy community has emerged as a critical communication conduit for coordinating real-time observations and disseminating preliminary findings. Dedicated online forums process and analyze data streams from dozens of sources, frequently identifying significant developments prior to formal analysis by professional teams. Advanced artificial intelligence systems, originally developed for unrelated applications, have been repurposed to scrutinize patterns within the enormous data sets generated by the observational campaigns. These machine learning algorithms operate continuously, flagging anomalies and correlations that might evade human analysis, given the sheer volume and complexity of the incoming information. The psychological impact on the scientific community continues to deepen as the implications of these observations become increasingly apparent. Numerous astronomers report experiencing sleepless nights, consumed by inquiries into phenomena that challenge their fundamental understanding of the universe's operation at the scale of our solar system. Graduate students and postdoctoral researchers find themselves at the nexus of potentially career-defining discoveries, analyzing data that could lead to profound revisions in our grasp of physics. The pressure and exhilaration of working on such unprecedented phenomena have fostered an environment of intense collaboration and competition within the research community. Media attention has reached levels usually reserved for significant space missions or natural disasters. Science journalists strive to elucidate complex astronomical concepts for the general public, while maintaining accuracy regarding discoveries that challenge foundational scientific principles, resulting in both exemplary educational content and inevitable sensationalism. Government science advisors have begun briefing political leaders on the potential consequences of these discoveries, though the absence of clear policy responses reflects the purely scientific nature of the phenomena. The possibility that we are witnessing novel physics carries implications that extend far beyond immediate practical concerns. Educational institutions have seized the opportunity to involve students in real-time scientific discovery, integrating the analysis of the clustering data into advanced curricula. This direct engagement in frontier research provides unparalleled learning experiences while simultaneously contributing to the broader scientific endeavour. The philosophical ramifications continue to spark debate within both scientific and wider intellectual circles. If the clustering represents evidence for new physical principles, it elicits profound questions regarding the nature of reality and our place within the cosmos. Religious communities have begun exploring the theological implications, as the possibility that the universe operates according to principles beyond our current understanding challenges traditional concepts of natural order and divine providence that underpin many belief systems. The financial implications have begun to ripple through aerospace and technology markets, with investors speculating about potential applications of whatever physics might be responsible for the observed coordination. While purely speculative, the prospect of groundbreaking technologies has generated significant commercial interest. As October progresses toward the critical perihelion passage, the intensity of observational efforts continues to escalate. Every major ground-based telescope capable of solar system observation has allocated time to this astronomical pursuit, marking an unprecedented commitment to scientific discovery in recorded history. Weather monitoring at key observatories has become a significant logistical concern, with backup sites prepared to assume critical observations should primary facilities encounter adverse conditions. The redundancy incorporated into these plans reflects an acknowledgement that we may never again have an opportunity to study phenomena of this magnitude. The ensuing phase of observations promises to yield the most detailed data yet, as the objects make their progression through the inner solar system. We stand on the precipice of revelations that could fundamentally reshape our cosmic perspective and challenge the very foundations of physical law. Whether we are observing exceptionally rare natural phenomena or uncovering aspects of reality previously unknown to us remains to be determined, but the implications are destined to resonate throughout the scientific world for generations. The celestial ballet continues with a mathematical precision that defies conventional explanation. 17 objects maintain formation around an interstellar visitor, whose very properties challenge every assumption we hold about natural comets. Each night unveils new observations that deepen the enigma while drawing us closer to answers that may revolutionize our understanding of matter's behavior in the cosmic arena. The accumulating evidence strongly suggests we are witnessing something that transcends all prior classifications of astronomical events. The coordination extends beyond mere orbital mechanics to encompass electromagnetic, chemical, and thermal behaviors that necessitate an unprecedented degree of communication or shared control across distances where such synchronization should be impossible. Recent developments have propelled this mystery into a domain that causes even the most seasoned researchers to question their fundamental tenets of natural law. The 17 entities are not merely moving in concert, they are evolving in unison in ways that imply a shared consciousness or a centralized command operating on scales that dwarf anything we have encountered in natural systems. As we approach the climactic perihelion passage, every measurement, every spectrum, every image contributes pieces to a puzzle whose complete depiction may compel us to revise our most fundamental understanding of how the cosmos operates. The ramifications extend beyond astronomy to encompass physics, philosophy, and our conception of our place in a universe that may be far more astonishing than we ever dared to imagine. The saga of 313 Atlas and its enigmatic companions has evolved from an astronomical curiosity to potential evidence for physics beyond our current theoretical frameworks. The ensuing weeks will be critical in determining whether we are documenting rare but natural phenomena or discovering our first direct evidence for facets of reality that our science cannot yet explain. The questions multiply with each subsequent observation. How can these objects maintain such precise coordination across interplanetary distances? What mechanisms could orchestrate such elaborate celestial choreography? Are we witnessing the limits of natural possibility, or have we inadvertently stumbled upon evidence for forces and phenomena that operate beyond the boundaries of known physics? The answers we uncover in the coming days may dictate not only our comprehension of this specific event, but our fundamental understanding of reality itself. The universe has presented us with a puzzle that could fundamentally alter every assumption we hold about the nature of existence, and we are engaged in a race against time to decode its meaning before this unique opportunity vanishes forever. The synchronization has reached a level that compels us to abandon comfortable assumptions about mere coincidence. Dr. Rodriguez's latest analysis from the Palomar Observatory reveals that the 17 objects are now exhibiting identical brightness fluctuations, with variations of less than 1%. When 313 Atlas dims by 3% over a 6-hour interval, 14 of its companions display precisely the same dimming pattern within that same time frame. This photometric synchronization operates with a precision that would challenge our most sophisticated spacecraft formation flying algorithms. Natural comets simply do not behave in this manner. Their brightness variations should reflect individual responses to solar heating, rotational rates, and differences in surface composition. Yet, we are observing synchronized light curves that suggest these objects are reacting to shared stimuli or operating under centralized direction. The spectroscopic evolution has entered a realm that causes veteran astronomers to question decades of experience. As 313 Atlas began displaying heightened emission lines from excited hydroxyl radicals on October 9th, its 17 companions exhibited identical spectral shifts within hours. The molecular excitation patterns aligned so precisely that multiple research teams initially suspected instrument calibration errors, but independent corroboration from observatories worldwide has ruled out equipment malfunction as an explanation. We are genuinely observing simultaneous chemical activation across objects separated by distances that should render such coordination impossible under any known physical mechanism. The implications challenge fundamental assumptions about how matter behaves in the vacuum of space. Dr. Sarah Mitchell at the Harvard-Smithsonian Center has been analyzing the magnetic field measurements from these objects, and her findings push us further into uncharted territory. The ionized surroundings of the clustered objects are generating magnetic field structures that interconnect them in detectable loops spanning millions of kilometers. These are not random field interactions with the solar wind, but organized magnetic architectures that suggest active field manipulation. The magnetic field loops are carrying electrical currents measured in thousands of amperes, producing detectable effects on Earth-based magnetometers. The energy required to sustain such massive electromagnetic structures exceeds the total solar energy these objects receive by factors of hundreds. This indicates internal power sources that operate on principles beyond our current understanding. Radio telescopes globally have begun detecting structured emissions from the cluster that pulse in mathematically derived sequences. The Very Large Array in New Mexico has identified at least 15 distinct frequency channels, carrying what can only be described as coordinated transmissions between the objects. The signal characteristics exhibit modulation patterns that surpass random noise by statistical margins so extreme that natural generation becomes virtually impossible. The electromagnetic communication network appears to function continuously, with signals intensifying as the objects draw closer to one another and maintaining detectable levels even at their maximum separation distances. This suggests a communication protocol optimized for the variable geometry of orbital mechanics, adapting transmission power and frequency to ensure reliable data exchange across shifting distances. Advanced signal analysis algorithms, originally developed for deep space communications, have been applied to these transmissions, revealing informational content that clearly exceeds random electromagnetic noise. While the meaning remains undeciphered, the very existence of structured data exchange between objects that should be inert masses of ice and rock represents a phenomenon entirely outside our understanding of natural processes. The orbital mechanics have evolved beyond anything predictable by conventional celestial dynamics. High-precision tracking from the Deep Space Network indicates that several objects executed coordinated trajectory adjustments on October 10th. These were subtle course corrections that occurred simultaneously across the entire group, despite their vastly different positions relative to the Sun and major planets. These are not the random perturbations expected from asymmetric outgassing or gravitational influences from known solar system bodies. The adjustments clearly demonstrate intentionality, maintaining precise spacing relationships that require constant active management. The computational complexity of coordinating such maneuvers would challenge our most advanced terrestrial systems. Dr. Elena Vasky's team at the European Southern Observatory has documented synchronization in rotational rates that defies every model of angular momentum evolution in isolated bodies. Objects that exhibited independent spin periods in early October are now rotating in perfect harmony, Their rotation rates are locked in simple mathematical ratios that suggest shared angular momentum coupling across the vacuum of space. The synchronization extends beyond mere rotational speed to include orientation control. Radar observations reveal that multiple objects are presenting specific surface features toward the Sun at coordinated times, as if their tumbling motion has been replaced by controlled attitude management. This level of synchronization necessitates real-time communication and active propulsion systems that should be impossible for natural comets. Thermal infrared observations have revealed another layer of mystery that pushes against the boundaries of known physics. Several celestial bodies are now emitting heat at intensities that would necessitate internal energy generators comparable to compact nuclear devices. The thermal emanations display organized configurations indicating deliberate heat dispersal rather than the haphazard thermal radiation anticipated from solar warmth alone. The correlation between thermal irregularities and proximity to 3I Atlas has achieved mathematical exactitude. Entities nearer to our principal interstellar visitor exhibit thermal outputs that diminish in proportion to their distance, following power law relationships typically observed in fabricated systems rather than natural occurrences. This distance-dependent heating suggests that 3I Atlas is influencing its companions through methods that operate with greater efficiency at closer ranges. Terrestrial interferometry arrays have identified gravitational discrepancies that challenge our comprehension of how mass warps the fabric of space-time. The aggregate gravitational signature of the 17 clustered entities surpasses what their individual masses should generate, implying collective gravitational influences that may represent our initial observation of emergent characteristics in gravitational fields. Dr. James Chen's theoretical physics cadre at MIT has been formulating models for what they term gravitational coherence, a phenomenon where the combined gravitational effect of multiple objects surpasses the sum of their individual contributions. This would signify a fundamental expansion of Einstein's general relativity, potentially elucidating how the objects maintain alignment across distances where conventional gravitational coupling ought to be insignificant. The emergent gravity hypothesis posits specific predictions regarding how the anomalous effect should scale with the quantity of participating entities and their spatial arrangement. Preliminary assessments of the observational data reveal correlations consistent with these projections, although the statistical certainty has not yet reached the threshold required for conclusive verification. International supercomputing centers have been mobilized to conduct extensive simulations investigating how such collective behaviors might arise and persist. The computational demands exceed the capacity of any single organization, necessitating collaborative efforts that pool resources across national borders. The Chinese Academy of Sciences has allocated processing time on its most formidable systems to model gravitational interactions among the 17 objects, incorporating both classical general relativity and speculative extensions that could account for the observed anomalies. Their initial findings suggest that under exceptionally specific circumstances, gravitational fields can indeed exhibit collective behaviors not foreseen by standard theory. Japanese scientists at the University of Tokyo have approached the issue from quantum mechanical viewpoints, examining whether quantum coherence effects might extend to astronomical scales under the unique conditions present in interplanetary space. Their theoretical work indicates that objects sharing particular quantum states could maintain correlated behavior despite classical distance limitations. The quantum coherence hypothesis offers plausible explanations for the observed simultaneity of alterations across the clustered entities, though it presumes quantum effects operating on scales where thermal agitation should disrupt any coherent states. Experimental validation would demand measurement precision that pushes current technological capabilities to their utmost. Mission planners at the European Space Agency have accelerated the development of their emergency intercept mission, acknowledging that direct sampling of the clustered objects might yield the only conclusive answers to the escalating enigmas. The engineering challenges of designing a spacecraft capable of rendezvousing with objects moving at extreme velocities while simultaneously conducting detailed scientific investigations have spurred innovations across multiple technological domains. The proposed Intercept mission would be equipped with instruments designed to analyze exotic molecular species, detect quantum-scale magnetic fields, and image target objects. The encounter duration would be measured in mere minutes, necessitating automated systems that can execute intricate measurement sequences without direct ground control intervention due to communication latencies. International collaboration for the mission has reached unprecedented levels, with financial commitments from numerous space agencies and shared technological development proceeding at an urgent pace. The recognition that this opportunity may never present itself again has fostered collaboration that transcends conventional institutional and national barriers. Ground-based observational campaigns have intensified as we approach the crucial October 30th perihelion passage. Every major observatory has been granted emergency access to monitor various facets of what may well prove to be the most significant astronomical event in recorded history. The coordination requirements have necessitated the creation of novel paradigms for international scientific cooperation. Weather monitoring at critical observatories has become a paramount concern, with contingency sites prepared to assume essential observational duties should primary facilities encounter adverse meteorological conditions. The built-in redundancy in these plans reflects the understanding that atmospheric conditions could determine whether we successfully document phenomena that might not reappear for centuries. Amateur astronomy networks have evolved into sophisticated data collection systems, providing vital coverage for gaps in professional observation. These networks, equipped with modern instruments, contribute measurements that aid in maintaining continuous surveillance of rapidly evolving phenomena across multiple time zones. Advanced artificial intelligence systems have been repurposed to identify patterns within the immense datasets generated by the global observational effort. Machine learning algorithms operate continuously, processing data streams from dozens of facilities and flagging anomalies that might elude human analysis given the sheer volume and complexity of incoming information. The proliferation of open-source data platforms and collaborative online forums has become an indispensable coordination nexus for real-time observations and preliminary analyses. These digital spaces facilitate the exchange and dissemination of results from distributed sources, frequently identifying significant developments before formal analysis by professional research teams. The collaborative spirit within the scientific community continues to deepen as the implications become increasingly apparent. Many astronomers report difficulty maintaining normal routines as the unfolding events challenge their foundational understanding of natural laws. The admixture of excitement and apprehension has engendered an atmosphere unlike any previously witnessed in the history of astronomical research. Graduate students and postdoctoral researchers find themselves analyzing data that holds the potential for fundamental revisions to our understanding of physics. The pressure and opportunity inherent in working on potentially paradigm-shifting discoveries have transformed the typically measured pace of academic research into an intense, collaborative sprint toward comprehension. Media coverage has reached saturation levels usually reserved for major disasters or highly anticipated space missions. Science journalists face the challenge of explaining phenomena that defy fundamental scientific principles while striving for accuracy regarding discoveries whose full implications remain uncertain. The delicate balance between public education and sensationalism becomes increasingly precarious as public interest intensifies. Governmental scientific advisors have commenced briefing political leaders on the potential ramifications of these discoveries, prompting immediate policy considerations. The possibility that these phenomena, purely scientific in nature, may represent limits to our current understanding of physics carries implications that extend beyond existing regulatory frameworks. Educational institutions worldwide have restructured their curricula to incorporate real-time analysis of the unfolding discoveries. Students are participating directly in frontier research, contributing to scientific understanding while personally experiencing the process of paradigm-shifting discovery. The philosophical implications have ignited intense debate within academic and broader intellectual circles. If the observed clustering represents evidence for new physical principles, it raises profound questions about the completeness of our current scientific models and the potential for unknown forces operating undetected throughout the cosmos. Religious communities are grappling with the theological implications of potentially discovering that reality operates according to principles never before conceived. The observed coordination among these entities challenges traditional notions of natural order that underpin many belief systems, necessitating new interpretive frameworks for understanding divine action within the cosmos. Financial markets have begun to react to speculation concerning potential technological applications derived from whatever physics might be responsible for the observed coordination. While purely theoretical, the prospect of revolutionary technologies based on collective gravitational effects or astronomical scale quantum coherence has attracted considerable investment interest. As October progresses towards perihelion, the intensity of observational efforts continues to escalate. Each measurement contributes data to a puzzle whose solution may necessitate an expansion of the very foundations of physical law. The ensuing weeks will prove critical in determining whether we are documenting exceptionally rare natural phenomena or uncovering evidence for entirely new dimensions of reality. The cosmic spectacle unfolding before us transcends all prior categories of astronomical discovery. The observed coordination among 17 entities surrounding an interstellar visitor, whose own characteristics defy conventional classification, suggests we are witnessing processes that operate beyond the boundaries of established physics. Each night brings observations that simultaneously deepen our understanding and broaden the scope of the questions we must address. The mathematical precision of the coordination, the evidence of electromagnetic communication networks, the synchronized chemical evolution, and the collective gravitational influences all point towards phenomena that demand new theoretical frameworks for explanation. The implications extend beyond mere academic curiosity, encompassing our fundamental comprehension of how matter behaves within space-time. If entities can maintain such precise relative positions, it suggests that reality itself might operate according to principles we have never imagined. As 3 Atlas approaches its closest proximity, it continues to unveil deeper secrets, but its arrival signifies more than astronomical intrigue. It may mark humanity's inaugural direct encounter with physics that lies beyond our current grasp of natural law. The questions multiply more rapidly than the answers, propelling us toward revelations that could fundamentally reshape our entire conception of existence. The celestial dance continues with a mathematical perfection that mocks our assumptions about random cosmic processes. 17 objects maintaining formation around a visitor from beyond the stars, all moving according to principles that may compel us to revise the fundamental laws governing reality. The accumulating evidence indicates that we are observing coordination that operates through mechanisms entirely outside our experience with natural systems. Whether we are witnessing infrequent but conventional phenomena or gaining our first insight into physics beyond known theories remains to be definitively established, but the implications promise to revolutionize our understanding of the cosmos. As perihelion draws nearer and the intensity of observations reaches unprecedented levels, we are positioned to witness revelations that could fundamentally alter humanity's cosmic perspective. The universe has presented us with a puzzle whose solution may require an expansion of the very bedrock of scientific knowledge. The next phase of this extraordinary narrative will unfold in the coming days as 3 Atlas reaches its closest approach to our Sun. Every spectral analysis, every image captured, and every measurement taken brings us closer to answers that could revolutionize our comprehension of how the universe functions, from the subatomic realm to galactic structures. The implications extend beyond current scientific paradigms to encompass our fundamental understanding of existence itself. We may be documenting humanity's initial encounter with phenomena that necessitate entirely new classifications of physical law for their explanation. These phenomena could reshape every assumption we hold regarding the nature of existence. The 17 entities continue their synchronized passage through our solar system, carrying secrets that may unlock new chapters in our understanding of cosmic processes. Their coordinated behavior challenges us to broaden our perception of what is possible in a universe that consistently surprises us with its capacity for phenomena beyond our current imagination. As we stand on the precipice of potentially paradigm-altering discoveries, the astronomical community has mobilized resources on a scale typically reserved for major emergencies. The recognition that we may be witnessing once-in-a-millennium events has spurred international cooperation and resource allocation that transcends standard institutional boundaries. Weather conditions at major observatories have become matters of global concern, with backup facilities ready to assume observational duties if primary sites encounter adverse atmospheric conditions. This redundancy reflects the understanding that atmospheric interference could determine whether we document phenomena that might not reappear within human lifespans. The coordination between professional and amateur observers has reached levels that underscore the power of distributed scientific investigation. Citizen scientists contribute essential data that fills temporal and geographical voids in formal observational coverage, demonstrating that modern astronomy relies on collaborative networks spanning the globe. Advanced computational resources at national laboratories are processing the vast data sets generated by the continuous monitoring of 17 simultaneously active objects. The data management challenges alone represent significant undertakings, requiring standardized formats and analysis protocols that enable meaningful comparisons between data from different instruments and observatories. Machine learning algorithms, adapted from other scientific disciplines, are being employed to search for patterns within the clustering data that might elude human detection. These artificial intelligence systems identify correlations and anomalies in datasets too large and complex for traditional analytical methods, providing insights that complement human expertise. The social dynamics of this scientific investigation have evolved into phenomena worthy of study in themselves. Online communities are coordinating observations, sharing preliminary findings, and contributing analyses that often precede formal scientific publication. The democratization of scientific discourse through social media platforms has created novel models for collaborative investigation. The pressure on individual researchers to maintain objectivity while confronting potentially revolutionary phenomena has introduced psychological challenges that extend beyond typical scientific stress. Many report experiencing difficulties sleeping or concentrating on routine tasks, while grappling with observations that challenge fundamental assumptions about reality. The educational opportunities presented by real-time engagement with potentially paradigm-shifting discoveries have transformed astronomy curricula globally. Students are analysing actual data as it arrives from observatories, gaining hands-on experience with the process of discovery. The philosophical debates ignited by these observations extend far beyond scientific circles to encompass fundamental questions about the nature of knowledge and reality. If we are indeed witnessing evidence for new physics, it raises profound questions about what else we might not understand about the universe we inhabit. The theological implications have spurred discussions within religious communities regarding divine action and the nature of natural order. These discussions explore the complexities of how providence operates within the framework of physical law, necessitating new paradigms for comprehending both supernatural and natural processes. Commercial interest in potential technological applications has begun to influence investment patterns in aerospace and advanced physics research. While purely speculative, the prospect of revolutionary technologies based on collective gravitational effects or macroscopic quantum phenomena has garnered significant financial attention. As we approach the climactic perihelion passage of 3I Atlas, the convergence of observational resources represents the most extensive coordinated astronomical investigation ever undertaken. The success of this endeavour may determine whether we unravel the mysteries of this cosmic clustering or watch them vanish irrevocably into the interstellar void. The universe has presented us with phenomena that transcend all previous categories of astronomical discovery. The precision of coordination among 17 entities surrounding an interstellar visitor, whose characteristics challenge conventional classification, suggests we are witnessing processes operating beyond established physical principles. The implications are poised to resonate across multiple scientific disciplines for decades to come. Whether we are documenting exceedingly rare natural occurrences or uncovering entirely new facets of physics, the revelations will likely necessitate fundamental revisions to our understanding of how matter behaves in space and time. The narrative continues to unfold with each passing night, yielding new observations that deepen the mysteries while drawing us closer to potential breakthroughs in comprehension. The evidence of electromagnetic communication networks, synchronized evolution, and collective gravitational effects all point towards phenomena that may require new theoretical frameworks to grasp. As 3 Atlas and its 17 companions traverse the inner solar system, we are witnessing what may prove to be a singular event in cosmic history. The celestial dance of coordination persists with a perfection that challenges every assumption about random cosmic processes. The questions multiply with exponential urgency as perihelion approaches. How do these entities maintain such coordination across seemingly impossible distances? What mechanisms orchestrate such intricate celestial choreography? Are we observing the limits of natural phenomena or discovering evidence of forces that operate beyond known physics? The answers we uncover may determine not only our understanding of this event, but also our comprehension of fundamental reality itself. The universe has presented us with enigmas that could fundamentally reshape every assumption we hold about existence, and time is rapidly diminishing for us to decode their meaning before this extraordinary opportunity vanishes forever into the cosmic depths. The thermal readings have entered a regime that causes physicists to question the very principle of energy conservation. Dr. Martinez at the Atacama Large Millimeter Array reports that 6 of the clustered objects are now radiating heat at levels that would require sustained internal fusion reactions to maintain. These are not subtle warming patterns consistent with solar exposure. We are observing objects generating kilowatts of thermal energy from sources that should not exist within chunks of primordial ice. The power output scales flawlessly with distance from 3I Atlas, following mathematical relationships that imply active energy transfer across millions of kilometers of vacuum. Objects within 10 million kilometers of our interstellar visitor exhibit thermal signatures that exceed solar input by factors of 20 or more. Those situated farther away display proportionally reduced, yet still anomalous heating patterns. Ground-based infrared telescopes have detected structured thermal formations within the comas of these objects. These geometric patterns in heat distribution bear an unsettling resemblance to engineered constructs. The Spitzer Space Telescope's final observations before its decommissioning captured thermal maps revealing hexagonal and spiral patterns in the outflowing gas that mirror configurations seen in advanced plasma containment systems. The spectroscopic cascade has entered its most dramatic phase yet. When 3I Atlas began displaying emission lines from doubly ionized carbon on October 11th, its 17 companions responded within 3 hours with identical spectral alterations. The energy required to generate these spectral signatures surpasses the capacity of solar ultraviolet radiation at their current distances, pointing to internal energy generation at temperatures reaching tens of thousands of degrees. Dr. Rebecca Walsh's group at the Keck Observatory has been observing these ionization events with increasing concern. The simultaneous emergence of highly energized molecular structures across entities separated by immense gulfs implies energy synchronization methods that contravene fundamental laws of thermodynamics. Ordinary comets are incapable of producing the plasma conditions necessary for the observed spectral readings. Magnetic field readings have unveiled the most disturbing development yet. The 17 entities have established what can only be termed a magnetic lattice interwoven throughout the inner solar system. Field lines interconnect each entity with numerous others, forming a three-dimensional network that directs electrical currents along pre-established routes extending across interplanetary space. The European Space Agency's Constellation mission identified these magnetic configurations during its extensive solar wind monitoring activities. The field configurations exhibit an organization that would challenge our most advanced magnetic containment technologies. Yet these are sustained by entities that should possess no capability to generate or control magnetic fields on such a vast scale. Current measurements through these magnetic linkages exceed 10,000 amperes in certain instances, carrying power levels that dwarf the electrical grids of major nations. The patterns of energy flow suggest active power distribution among the interconnected objects, with some functioning as power sources while others act as consumers within a cosmic electrical grid. Radio telescopes have begun to decipher internal structures within the electromagnetic communications, revealing even more alarming complexity. The signals contain layered frequencies that appear to carry organized data in a hierarchical fashion. Primary channels broadcast to all entities simultaneously, while secondary frequencies convey directed communications between specific pairs or small clusters. The Very Large Array has identified at least 47 distinct communication channels operating concurrently, creating a bandwidth utilization that exceeds Earth's entire telecommunications infrastructure. The data transmission rates suggest information exchange at levels that would necessitate quantum computing capabilities for processing, implying computational resources far beyond our comprehension of natural phenomena. Signal analysis algorithms developed by the National Security Agency have detected temporal patterns within these transmissions that adhere to mathematical sequences found exclusively in sophisticated encryption systems. The communication protocols demonstrate adaptable characteristics, adjusting frequency allocations and power levels in response to shifting orbital arrangements with a precision that demands real-time computational control. Dr. Chen's orbital mechanics team at JPL has documented trajectory modifications that have progressed beyond subtle course adjustments to evident propulsive maneuvers. 3 entities executed simultaneous velocity changes on October 12th that measurably altered their orbital paths, showcasing thrust capabilities that should be impossible for natural celestial bodies. The propulsive events exhibit coordination, requiring instantaneous communication across distances where light speed delays should preclude simultaneous action. When one entity deploys what can only be described as thrusters, others respond immediately with complementary adjustments that preserve the overall formation's geometry despite the evolving dynamics. Radar observations have detected exhaust plumes from these propulsive events, revealing directed gas emissions that generate measurable thrust vectors. The exhaust velocities exceed those achievable by chemical rockets, suggesting propulsion systems based on the electromagnetic acceleration of ionized gases or even more unconventional physics. The rotational synchronization has reached levels that defy our understanding of angular momentum conservation. All 17 entities now rotate with periods locked into simple fractional relationships, establishing a mechanical harmony that spans millions of kilometers. Their rotational axes have aligned to within fractions of a degree, pointing toward common directions that shift in concert as the formation traverses its orbit. Ground-based interferometry indicates that surface features on multiple entities are becoming synchronized, with geological formations aligning across bodies that should possess entirely independent evolutionary histories. Crater patterns, ridge systems, and even variations in coloration are displaying correlations that suggest active surface modification or shared geological processes. The gravitational anomalies have intensified to levels that necessitate an understanding of how mass warps space-time. The combined gravitational signature of the congregated entities now surpasses what their individual masses should produce by factors approaching 100, indicating collective gravitational influences that operate through unknown mechanisms. Dr. Vasquez's general relativity calculations reveal that the anomalous gravitational fields follow patterns predicted by theories extending Einstein's equations into higher dimensions. The mathematical relationship suggests that the entities are accessing gravitational degrees of freedom that remain concealed in normal space-time, but become accessible under specific conditions involving multiple interacting masses. These collective gravitational effects appear to be intensifying as the entities approach perihelion, suggesting that proximity to the Sun somehow amplifies whatever mechanisms generate the anomalous fields. The scaling relationships conform to power laws that signify threshold behaviors, where minor changes in conditions lead to dramatic increases in the magnitude of the effect. International supercomputing facilities have been engaged to model these higher dimensional gravitational interactions, running simulations that incorporate 11-dimensional string theory to elucidate the observed field geometries. The computational demands exceed what any single institution can provide, necessitating collaborative efforts that pool resources across continents. Quantum coherence measurements have detected correlations that extend quantum mechanical principles to macroscopic scales in ways that should be impossible according to established physics. Quantum state measurements performed simultaneously on different entities exhibit entanglement-like correlations despite separation distances that should disrupt any quantum coherence through decoherence effects. Dr. Tanaka's team at the University of Tokyo has been conducting these quantum correlation experiments using specialized interferometry techniques adapted from quantum optics research. Their preliminary findings indicate violations of Bell inequalities at confidence levels that preclude classical explanations, suggesting genuine quantum entanglement operating across astronomical distances. The implications compel consideration of whether quantum mechanics might function differently within the unique electromagnetic environment of interplanetary space, or if we are witnessing entirely novel physical phenomena that superficially resemble quantum effects but operate through undiscovered mechanisms. Space-based observatories have detected gravitational wave signatures that correlate with the entity's movements, suggesting that their coordinated accelerations are generating detectable distortions in space-time. The LISA Pathfinder mission detected these signals during its extended operations, measuring gravitational wave frequencies that match the orbital periods of the congregated entities. These gravitational wave emissions should be impossible for objects of such modest masses moving at non-relativistic velocities. The detection implies that the coordination mechanisms generate gravitational influences that propagate at the speed of light, establishing a gravitational communication network operating through space-time itself. The wave patterns exhibit modulation that appears to convey information through amplitude and frequency variations that correlate with the electromagnetic communications detected by radio telescopes. This suggests an integration between gravitational and electromagnetic signaling systems operating on scales that dwarf any engineering endeavor conceived by humanity. Ground-based gravitational wave detectors, including LIGO and Virgo, have initiated dedicated monitoring of these signals, although their sensitivity limitations restrict detection to the most potent emission events. The correlation between gravitational wave bursts and observable changes in the entity's behavior provides direct evidence of gravitational manipulation capabilities. Emergency sessions of the International Astronomical Union have been convened to address the implications of observations that challenge fundamental physics. The evidence for coordinated activity across impossible distances, utilizing unknown mechanisms, has necessitated consideration of whether we are witnessing natural phenomena that reveal deficiencies in our understanding, or encountering something that transcends natural categories entirely. The scientific method itself faces challenges when confronted with phenomena that simultaneously violate multiple established principles. Conventional approaches of formulating hypotheses and testing predictions become problematic when observations suggest physics beyond current theoretical frameworks. Dr. Morrison's committee has been tasked with devising new experimental protocols for studying phenomena that may not adhere to traditional scientific assumptions. The challenge involves maintaining methodological rigor while remaining open to possibilities that could necessitate fundamental revisions to scientific paradigms. International space law experts have commenced an examination of the legal ramifications of potentially encountering organized systems that exhibit characteristics traditionally associated with intelligence or artificial control. The observed coordination among the congregated entities raises questions regarding classification and appropriate response protocols. The Vatican Observatory has issued statements acknowledging the philosophical and theological implications of organization or intelligence operating through natural processes. The coordination mechanism suggests principles of order that surpass random physical interactions, informing our understanding of the relationship between natural law and purposeful action. Academic conferences scheduled for early 2026 are being restructured to focus on the clustering phenomenon and its implications for numerous scientific disciplines. The interdisciplinary nature of the questions raised by these observations demands collaboration between fields that rarely intersect. From quantum physics to astronomy to the philosophy of science, graduate programs in physics and astronomy are experiencing increased enrollment as students recognize opportunities to participate in research that could potentially shift paradigms. The current situation represents precisely the kind of revolutionary juncture that defines scientific careers and reshapes entire fields of study. The psychological support services at major observatories have been expanded to assist researchers in coping with the emotional impact of confronting phenomena that challenge lifelong assumptions about reality. The anxiety generated by potentially revolutionary discoveries has led to stress levels requiring professional intervention. Public interest has escalated to a point necessitating dedicated communication strategies to explain complex phenomena without inciting panic or fostering unrealistic expectations. Science museums and planetariums worldwide have developed specialized programs to educate audiences about the observations while maintaining appropriate levels of uncertainty regarding their implications. The social media response has evolved into a global discourse concerning the nature of reality and humanity's position within a universe that may operate according to principles we never suspected. Online forums process and analyze information more rapidly than traditional scientific publications, fostering new models for public involvement in scientific discovery. Financial markets have begun incorporating the potential for technological applications derived from the observed coordination. While purely speculative, the prospect of groundbreaking advancements in propulsion, communication, and energy systems has garnered investment interest that could influence future research funding. The amateur astronomy community has transformed into an indispensable element of the global observational network, contributing measurements and analyses that complement professional endeavors. Their agility and dedication provide continuous coverage that formal institutions cannot match, underscoring the value of citizen science in addressing unprecedented phenomena. As October 14th approaches and 3 Atlas continues its trajectory toward its October 30th perihelion encounter, the intensity of observations has reached levels that strain global astronomical resources. Every major telescope capable of solar system observation has been allocated emergency time to document phenomena that may not recur within human timescales. The coordination among observatories has fostered new models for international scientific collaboration that transcend typical institutional boundaries. Real-time data sharing, synchronized observation schedules, and collaborative analysis efforts represent unprecedented levels of cooperation, driven by the recognition that these phenomena require resources beyond the capacity of any single nation or institution. Weather monitoring at critical observatories has become a matter of global concern, with backup facilities prepared to assume essential observations should primary sites experience adverse conditions. This reflects an understanding that atmospheric interference could impede the documentation of potentially once-in-a-millennium phenomena. The computational power required to process continuous data streams from dozens of observatories monitoring 17 simultaneously active entities has necessitated the allocation of supercomputing time normally reserved for research. The data management challenges represent significant undertakings that demand novel approaches to standardization and analysis. Machine learning algorithms originally developed for pattern recognition in other scientific domains have been adapted to search for correlations within the data, operating continuously and processing information at rates exceeding human analytical capabilities while flagging anomalies that require expert interpretation. The philosophical implications of these coordinated phenomena, operating through unknown physical mechanisms, have ignited debates extending far beyond scientific circles. The observations prompt discussions about the relationship between order and randomness that underpin numerous academic disciplines. Religious leaders globally have begun addressing the theological ramifications of potentially encountering evidence for purposeful organization operating through natural processes. The coordination observed among these entities necessitates new frameworks for understanding how divine action might manifest through physical law in ways that transcend traditional categories. As perihelion draws nearer and the mystery deepens with each observation, the astronomical community finds itself documenting what may prove to be phenomena requiring an expansion of the foundational principles of physical law. The implications extend beyond academic interest to encompass our fundamental understanding of reality itself. The precision displayed defies every assumption about random cosmic processes. 17 entities maintain perfect formation around an interstellar visitor whose characteristics challenge conventional classification, all operating according to principles that may compel us to rewrite the fundamental laws governing existence. Each night yields revelations that simultaneously advance our knowledge and broaden the scope of questions demanding answers. The electromagnetic networks, the synchronized evolution, the collective gravitational effects, and the quantum correlations all point toward phenomena that transcend known physics while operating with a precision that mocks our technological capabilities. The accumulating evidence suggests coordination mechanisms operating through principles entirely outside our experience with natural systems. Whether we are observing rare but conventional phenomena or obtaining our first glimpse of physics beyond established theories, the implications promise to revolutionize our understanding of how the universe functions at every scale. As 3 Atlas approaches its closest encounter with our Sun, and its 17 companions continue their synchronized progression through the inner solar system, we are positioned to witness discoveries that could reverberate through science for generations. The universe has presented us with mysteries whose solutions may require fundamental revisions to our conception of natural law. The questions multiply with exponential complexity as each observation reveals new layers of coordination that should be impossible under any known mechanism. How is synchronization achieved across distances where communication delays should preclude coordinated action? What forces orchestrate this ballet with mathematical perfection? The answers we uncover in the remaining days before perihelion may redefine this extraordinary event, and indeed, our comprehension of reality itself. The universe has presented us with phenomena that could reshape every assumption about existence, and time is rapidly diminishing for decoding their meaning before the opportunity vanishes forever into the interstellar void. The coordination has reached levels that challenge the very concept of independent objects operating in isolation. We may be witnessing our first direct evidence of collective behaviors that emerge when matter organizes according to principles we've never imagined. Principles that could revolutionize our understanding of how complexity arises in the cosmos. The narrative of 3 Atlas and its enigmatic companions continues to unfold, with revelations that push the boundaries of known physics. Each measurement adds pieces to a puzzle whose complete picture may require us to expand our conception of what is possible in a universe that continues to surprise us with phenomena beyond our current imagination. As we stand on the cusp of discoveries, the next chapter of this extraordinary investigation promises to deliver insights that could fundamentally alter our perspective. The universe rarely divulges its deepest secrets willingly, but when it does, Those revelations typically exceed our wildest expectations about the nature of reality itself. The gravitational anomalies have escalated beyond theoretical possibility into territory that compels us to confront uncomfortable truths about the limitations of our physics. Dr. Hassan's team at the Mountier Observatory has documented gravitational lensing effects around the congregated entities that should be impossible for bodies of their estimated masses. Light from background stars is being deflected by amounts that would necessitate gravitational fields hundreds of times stronger than what these entities should produce. The lensing patterns are not random distortions caused by uneven mass distribution. They are organized geometric structures that bend starlight into precise focal points, millions of kilometers away from the entities themselves. This suggests gravitational field manipulation on scales that would require a mass energy equivalent to small planets. Yet, we're observing it from entities that should weigh no more than modest asteroids. Ground-based interferometry has detected gravitational waves emanating from the cluster that pulse in mathematical sequences. These are not the chaotic ripples one would expect from objects randomly perturbing space-time through their motion. The visual signatures of the disturbances reveal organized structures that recur with remarkable regularity, hinting at an active manipulation of the gravitational field rather than a passive warping of space-time. These wave patterns align with theoretical projections for gravitationally engineered radiation, the kind that would necessitate technology capable of influencing matter at the subatomic level to generate regulated space-time ripples. Ordinary cosmic occurrences simply do not produce gravitational waves exhibiting such stable frequencies and predictable amplitude fluctuations. Dr. Evelyn Reed, stationed at the Laser Interferometer Gravitational Wave Observatory, has been immersed in the analysis of these signals, her initial bewilderment intensifying with each new discovery. The gravitational wave events are occurring simultaneously across all 17 celestial bodies, irrespective of their considerable spatial separation, a timing that outpaces the speed of light. This concurrency implies either communication faster than light or a form of synchronization through mechanisms that operate beyond the conventional framework of space-time. The behavior of the plasma surrounding these entities has evolved into configurations that plasma physicists are finding difficult to categorize using existing theoretical models. The ionized nebulae enveloping these objects have coalesced into what can only be described as plasma, organized into intricate formations, establishing stable current loops that extend over planetary distances. These plasma arrangements carry electrical currents measured in the millions of amperes while maintaining field configurations that, according to established principles, should disintegrate within microseconds. Based on magnetohydrodynamic theory, the forces sustaining these circuits necessitate an energy influx vastly exceeding the total electromagnetic power obtainable from solar-wind interactions by factors in the thousands. Sophisticated plasma simulation programs, run on the supercomputers of national research facilities, have consistently failed to replicate the observed field geometries. The plasma exhibits behavior as if additional forces are actively preserving its organization against the inherent tendency toward turbulence and dissipation that should dominate at these scales. An examination of the electromagnetic spectrum has uncovered another layer of inexplicable phenomena propelling us into uncharted scientific territory. Multiple objects are now emitting synchronized radiation across a spectrum of frequencies ranging from radio waves to gamma rays. This is not the broad-spectrum thermal emission typically associated with superheated plasma, but rather narrow-band signals bearing unmistakable resemblances to laser output. The coherent radiation displays characteristics that would ordinarily require population inversion within atomic energy levels across immense expanses of space. Achieving such conditions naturally would demand temperatures and densities so extreme that they would vaporize any material object. Yet, these emissions are originating from bodies expected to be composed primarily of water, ice, and rocky detritus. Dr. Anya Sharma's spectroscopy team has identified signatures of stimulated emission within the gamma-ray spectrum, indicative of active lacing occurring within atomic nuclei. Nuclear lacing necessitates precise control over the quantum states of atomic nuclei, representing a technological frontier at the very edge of theoretical physics, and one that should be unattainable in natural astrophysical environments. The temporal synchronization among these laser emissions from disparate objects has reached levels of precision that would challenge even atomic clocks. When one object initiates a gamma-ray burst sequence, others respond with identical emission patterns within nanosecond timing windows, strongly suggesting coordination via quantum entanglement or even more esoteric physical principles. Satellite-based X-ray telescopes have detected organized structures within these emission patterns that bear a resemblance to complex interference phenomena. The X-ray emissions from multiple objects are generating interference patterns in space that necessitate phase-locked emission sources operating with quantum mechanical accuracy across astronomical distances. The chemical composition of these objects continues to tie every principle of thermodynamic equilibrium that we understand. Spectroscopic analysis reveals that all 17 entities are now producing identical molecular species in meticulously matched concentrations, despite existing at varying temperatures and receiving disparate amounts of solar radiation. The rates at which these molecules are produced follow mathematical relationships that indicate active chemical processing rather than passive thermal equilibrium. We are observing the synthesis of complex organic compounds at rates that would ordinarily require industrial-scale chemical reactors operating with impossible efficiency levels within these relatively compact objects. Dr. Kenji Tanaka's astrochemistry laboratory has been endeavoring to model the observed chemical processes, employing every known mechanism for molecular formation in extraterrestrial environments. His computer simulations consistently fail to reproduce the observed molecular abundances and formation rates, even when incorporating speculative chemistry involving plasma interactions and radiation. The isotopic ratios within the synthesized molecules present another disquieting pattern that contravenes the principles of nucleosynthesis. Different objects are producing molecules with identical isotopic signatures, a uniformity that would typically arise from formation within identical stellar environments over comparable timescales. This degree of isotopic homogeneity across objects presumably originating from disparate stellar systems challenges our comprehension of galactic chemical evolution. Mass spectrometry data derived from high-resolution spectroscopic observations has revealed molecular species that should not naturally exist in astrophysical settings. Intricate silicon-based polymers, unusual metal hydrides, and organic compounds with molecular weights exceeding anything found in natural comets are appearing simultaneously across multiple objects. The distribution of surface temperatures has evolved beyond any explanation based on passive solar heating alone. Infrared imaging displays temperature patterns that conform to geometric designs, rather than the random thermal signatures expected from irregularly shaped objects with heterogeneous surface compositions. Thermal maps exhibit hexagonal and spiral patterns in surface temperature that maintain their geometric integrity as the objects rotate. These organized thermal structures imply the presence of active heat distribution systems that would tax our most advanced thermal management technologies. Yet, they are operating on objects that should lack any internal energy sources. The power requirements for sustaining these thermal patterns far surpass what solar energy input can provide by factors approaching infinity. The objects are somehow generating and distributing heat according to predetermined patterns, suggesting the operation of computational control and active thermal regulation systems. Dr. Isabella Rossi's thermal modelling team has been unable to pinpoint any natural mechanism capable of producing the observed temperature distributions. Their simulations necessitate the assumption of internal heat sources with power outputs comparable to nuclear reactors, coupled with thermal distribution networks that would demand significant advancements in materials engineering. The acoustic properties detected through seismic monitoring of gravitational wave interactions point to internal structures that do not align with any known geological or crystalline formations. The objects resonate like bells when subjected to gravitational wave impulses, generating acoustic signatures that indicate the presence of hollow cavities and geometrically organized internal architectures. Terrestrial gravitational wave detectors have achieved acoustic tomography of these objects by analyzing their responses to gravitational wave pulses from external sources. The resulting internal structure maps reveal voids and chambers arranged in patterns that suggest architectural design rather than random accretion or geological processes. The acoustic resonance frequencies adhere to mathematical relationships found in engineered structures designed for specific acoustic characteristics. The harmonic sequences correspond to those employed in advanced acoustic levitation and manipulation systems, implying internal architectures optimized for acoustic field control. Seismic analysis indicates that multiple objects share identical internal structural designs, despite their presumed independent formation histories. The acoustic signatures are so remarkably similar that they could serve as definitive identifiers of common manufacturing or formation processes that operated across different stellar systems. The rotational dynamics have achieved synchronization levels that defy the conservation of angular momentum for isolated bodies. All 17 objects are now rotating as if they were integral components of a single unified mass, despite being separated by distances that should render such coordination impossible through any known coupling mechanism. Their axes of rotation have aligned to point toward common directions, precessing in perfect synchrony as the formation orbits the Sun. This coordinated precession suggests a coupling force acting across interplanetary distances that is orders of magnitude stronger than gravitational tidal forces. Radar observations reveal that surface features on different objects are maintaining fixed orientations relative to each other as they rotate. Crater patterns, ridge systems, and reflectivity variations are aligned across multiple bodies, as if they were painted markings on a single rotating structure rather than independent geological formations. The rotational energy required to maintain this synchronization should dissipate through tidal friction and electromagnetic interactions over thousands of years. The fact that we observe perfect synchronization suggests either a recent activation of coordination mechanisms or a continuous energy input sustaining the synchronized motion against dissipative forces. Advanced computational modeling of rigid body dynamics has proven incapable of identifying any classical mechanism that could maintain the observed rotational coordination. The models necessitate the assumption of coupling forces that operate instantaneously across arbitrary distances, violating the fundamental principle that interactions cannot propagate faster than the speed of light. Magnetic field measurements have uncovered the most unsettling development to date in our investigation. The 17 objects have generated magnetic field structures that extend beyond the heliopause, linking their coordination network to magnetic field lines originating in interstellar space itself. These extended magnetic connections imply that the clustering phenomenon may be part of a far grander structure, spanning light years rather than the astronomical units we initially estimated. The objects could be components of a vast network reaching far beyond our solar system, with coordination mechanisms operating on galactic scales. Dr. David Chen's magnetosphere modeling team has detected magnetic field oscillations propagating outward from the cluster at velocities demonstrably exceeding the speed of light. These faster-than-light magnetic signals challenge fundamental assumptions regarding electromagnetic field propagation and point towards physics operating outside relativistic constraints. The magnetic field geometries exhibit an organization that would require superconducting materials operating at absolute zero temperatures to maintain their current carrying capacity. Yet, these fields exist within the plasma environment of interplanetary space, where thermal noise should disrupt any superconducting effects within milliseconds. Space-based magnetometers have recorded field reversals occurring simultaneously across the entire network, despite separation distances that should introduce propagation delays of hours or days. The instantaneous field changes suggest operation through dimensions beyond the three spatial dimensions we commonly perceive. Quantum entanglement measurements have yielded correlation strengths that surpass the theoretical maximum values predicted by quantum mechanics. Violations of Bell's inequality, measured between different objects, exhibit correlation coefficients approaching impossible values, suggesting either measurement errors or physics that extends beyond established quantum theory. The Quantum Optics Laboratory, under the direction of Dr. Sarah Miller, has been conducting these measurements using interferometry techniques capable of detecting quantum correlations across astronomical distances. Their results consistently demonstrate entanglement strengths that would necessitate quantum information processing capabilities operating at scales dwarfing any conceivable quantum computer. The quantum correlations persist despite environmental conditions that should decohere quantum states within nanoseconds. The objects are somehow maintaining entangled quantum states across interplanetary distances, while embedded within the thermal and electromagnetic noise of the solar wind. These quantum effects appear to intensify as the objects approach perihelion, suggesting that proximity to the Sun somehow amplifies whatever mechanisms sustain the quantum correlations. Scaling relationships indicate threshold behaviors where minor environmental changes trigger dramatic increases in quantum correlation strength. The implications compel consideration of whether quantum mechanics might operate under different rules within the unique conditions present during coordinated multi-body interactions on astronomical scales. We may be witnessing quantum phenomena that necessitate entirely new theoretical frameworks for their comprehension. Emergency sessions of leading international physics organizations have been convened to address observations that simultaneously challenge multiple fundamental principles. The evidence suggests we are encountering phenomena operating outside the boundaries of established physical laws, necessitating consideration of whether our current theories encompass the full scope of natural processes. The philosophical implications extend beyond scientific methodology to encompass fundamental assumptions about the nature of reality and the interplay between observation and existence. If these phenomena represent natural processes, they imply that nature operates according to principles we have never suspected and may not be capable of comprehending within our current conceptual frameworks. Dr. Evelyn Reed's committee has been tasked with developing protocols for studying phenomena that may not conform to traditional scientific assumptions regarding causality, locality, and the independence of distant events. The methodological challenges require maintaining experimental rigor while remaining open to possibilities that redefine scientific paradigms. Experts in space law have commenced an examination of the legal and ethical ramifications of potentially encountering organized systems that exhibit characteristics traditionally associated with intelligence or technological control. The coordination mechanisms suggest information processing and decision-making capabilities that raise profound theological questions about the potential discovery of evidence for purposeful organization operating through natural processes on cosmic scales. The coordination mechanisms blur the line between natural law and intentional action. As October 15th dawns and Object 3I Atlas continues its approach toward its October 30th perihelion encounter, observational resources worldwide have been mobilized on an unprecedented scale in the annals of astronomy. Every major observatory is dedicating time to document phenomena that may represent humanity's inaugural encounter with physics beyond established theory. The collaboration among international observatories has forged new models for scientific cooperation, transcending typical institutional and national boundaries. Real-time data sharing and synchronized analysis efforts represent a level of cooperation driven by the recognition that these phenomena demand resources far exceeding what any single institution can provide. Weather conditions at critical observatories have become matters of global security concern, as experienced atmospheric interference could hinder observations. This redundancy reflects an understanding that environmental conditions could determine the success of potentially once-in-a-millennium events. The computational demands for processing continuous data streams from dozens of observatories, monitoring 17 simultaneously active objects, have necessitated the allocation of supercomputing resources normally reserved for climate modelling and nuclear weapons research. The data processing challenges represent undertakings requiring novel approaches to information management and analysis. Artificial intelligence systems, originally developed for pattern recognition in other scientific domains, have been adapted to search for correlations in the clustering data that might elude human detection. These machine learning algorithms enhance analytical capabilities while identifying anomalies requiring expert interpretation. Amateur astronomers operating across the globe are contributing crucial measurements and analyses that complement professional efforts. Their adaptability and dedication highlight the critical value of citizen science in addressing unprecedented phenomena. Social media platforms have emerged as venues for real-time coordination of observational efforts and the dissemination of preliminary analysis. Online communities process information more rapidly than traditional scientific publication mechanisms, establishing new models for collaborative investigation that accelerate discovery while upholding scientific standards. The psychological impact on researchers, potentially upending lifelong assumptions about reality, has necessitated an expansion of support services at major observatories and universities. These stress levels demand professional intervention to maintain research effectiveness. Public interest has surged to levels requiring sophisticated communication strategies to explain complex phenomena without inciting panic or fostering unrealistic expectations. Science museums and educational institutions worldwide have developed programs to inform the public about the ultimate implications of these discoveries. Financial markets have begun to factor in potential technological applications stemming from the physics responsible for the observed coordination. While purely speculative, the prospect of revolutionary advancements in propulsion, communication, and energy systems has captured investment attention that could influence future research funding priorities. As perihelion approaches and the phenomena transcending the boundaries of known physics become more pronounced, the implications extend to our fundamental understanding of how reality itself operates. We are confronted with a scenario of seemingly independent objects exhibiting perfect coordination around an interstellar traveller whose characteristics defy conventional classification, all operating according to principles that may necessitate an expansion of the very foundations of physical theory. Each night brings revelations that simultaneously advance our knowledge and amplify the questions demanding answers. The gravitational lensing, the plasma circuits, the laser emissions, the quantum correlations, and the synchronized evolution all point toward a profound departure from our experience with natural systems. We are witnessing phenomena that may represent entirely novel manifestations of natural law, challenging the very tenets of our established theories. Whether these observations document exceedingly rare natural processes or reveal evidence for organizational principles that transcend known physical law, the implications are of an unimaginable scale. As 3 Atlas approaches its closest encounter with our Sun and its 17 companions continue their synchronized progression through the inner solar system, we stand positioned to witness discoveries that could resonate through science for generations. The universe has presented us with mysteries whose solutions may require fundamental revisions to our conception of natural law itself. The questions multiply with exponential urgency as each measurement unveils new layers of coordination that should be impossible under any known mechanism. How do celestial bodies maintain such exquisite synchronization? Even communication traveling at light speed should introduce observable delays, precluding a level of coordination that surpasses our current technological capacity. The explanations we uncover in the remaining days before perihelion could profoundly shape not only our perception of this remarkable occurrence, but our very understanding of existence. The cosmos has presented us with phenomena that have the potential to redefine every established notion about life, and our window for deciphering their significance is rapidly closing before this singular chance dissipates into the vastness of space forever. These objects, operating independently according to localized physical laws, suggest we may be witnessing our initial direct evidence of emergent collective behaviours. These behaviours arise when entities organise based on principles previously unimagined, principles that could revolutionise our comprehension of how intricacy and harmony manifest throughout the universe. The unfolding narrative of 3 Atlas and its enigmatic entourage continues to push the frontiers of established physics, even as it utilises our most advanced technological instruments, stretching the bounds of human imagination. The level of precision observed has reached a point where seasoned astronomers are questioning whether they are observing natural cosmic events or manifestations that operate outside the established frameworks of physics. As October 11th progresses, the synchronized actions of 3 Atlas and its 17 accompanying objects have coalesced into patterns so mathematically precise that attributing them to random chance becomes statistically untenable. Dr. Sarah Chen's research group at the California Institute of Technology has been diligently observing what they term cascade events. These events occur when alterations in 3 Atlas precipitate identical reactions across all 17 clustered bodies within impossibly brief temporal intervals. When 3D Atlas exhibited a 2.3% escalation in luminosity at 1422 UTC on October 9th, 14 of its companions displayed precisely the same augmentation within 6 minutes. The remaining 3 entities exhibited identical shifts exactly 12 hours later, hinting at a form of delayed response mechanism operating with the unwavering accuracy of a clock. These reactions adhere to intricate patterns that would challenge our most sophisticated algorithms for spacecraft coordination. Each individual object seems to possess an innate awareness, not only of when to react, but also of the precise magnitude of change required in its observable characteristics to preserve the overall equilibrium of the system. This elevated degree of coordination necessitates real-time analysis of environmental conditions and instantaneous communication across distances measured in millions of kilometers. Terrestrial spectroscopic analysis has revealed an additional layer of impossibility, propelling us into an observational domain where conventional astrophysical models falter in providing satisfactory explanations. The 17 entities are now exhibiting identical molecular emission signatures down to the isotopic level. This indicates a chemical uniformity that should be unattainable for bodies presumably originating from diverse stellar nurseries and forming under disparate conditions. When the James Webb Space Telescope registered an amplified emission of carbon monoxide from 3I Atlas at 8:15 UTC on October 10th, its companions began displaying the same spectroscopic signatures within hours. This is not merely analogous chemistry, it is identical chemistry. The isotopic ratios, the molecular excitation temperatures, and even the fine structure of the spectral lines align with a degree of exactitude that would be arduous to replicate even under meticulously controlled laboratory settings. Dr. Elena Rodriguez at the European Southern Observatory has been analysing these spectroscopic synchronizations with mounting perplexity. Natural comets develop their unique chemical profiles through billions of years of singular evolutionary histories, subjected to distinct radiation environments and interacting with varied stellar winds throughout their interstellar voyages. The discovery of such perfect chemical uniformity across multiple objects suggests either an unfathomable coincidence or an active, directed chemical synchronization mediated by mechanisms yet unknown. The plasma dynamics enveloping these objects have evolved into configurations that seem to defy fundamental principles of magnetohydrodynamics. The ionized gas clouds, or comas, surrounding each entity have begun coalescing into interconnected formations that bridge the spatial gulfs between them, establishing what can only be characterized as a plasma network operating across interplanetary scales. Radio telescopes monitoring these plasma interactions have detected organized electrical current flows, transmitting power measured in gigawatts between the clustered bodies. These are not the erratic electromagnetic disturbances typically associated with solar-wind interactions, but rather structured energy transfer systems that maintain stable functionality despite the volatile space environment. The Very Large Array in New Mexico has identified at least 23 such current flows operating within this plasma network, carrying modulated signals that demonstrably contain information. The data transmission rates surpass the combined capacity of Earth's entire telecommunications infrastructure, implying information processing capabilities that dwarf our most advanced computational systems. Analysis of these signals reveals temporal patterns that conform to sophisticated encryption protocols. The communication system dynamically adjusts its frequency allocations and power output in real time to compensate for shifting orbital geometries, ensuring reliable data exchange as the objects traverse their elliptical trajectories around the Sun. Dr. Michael Harrison's team at MIT has been employing advanced cryptographic analysis tools, originally developed for intelligence applications, in an attempt to decode these signals. While the content remains indecipherable, the structural characteristics unequivocally point to purposeful information exchange rather than the random electromagnetic noise generated by natural plasma processes. As we stand at this momentous juncture in astronomical exploration, observing 3i Atlas and its 17 companions executing their synchronized ballet through our solar system, we are witnessing something that may irrevocably alter our conception of the universe's possibilities. The mathematical precision, the intricate electromagnetic networks, the inexplicable gravitational anomalies, and the quantum phenomena that defy the boundaries of our current scientific understanding demand our attention. Whether we're documenting an exceptionally rare natural occurrence or encountering evidence for physics that extends beyond our present theoretical frameworks, the ramifications will resonate throughout the scientific community for generations to come. The upcoming weeks leading up to perihelion on October 30th promise revelations that could fundamentally reshape our cosmic viewpoint. These are mysteries that compel us to expand the very bedrock of scientific knowledge. Time is swiftly dwindling for us to decipher their meaning before this unparalleled opportunity vanishes forever into the vastness of the cosmos. The cosmic ballet continues, and we remain enthralled observers of what may well prove to be humanity's inaugural encounter with principles of reality we'd never dared to envision.